Have you ever looked up at the night sky and felt a deep, almost primal sense of wonder, a quiet curiosity about what lies beyond the stars we can see? It's a question that has echoed through human history, from ancient stargazers to modern physicists, and today, we're closer than ever to uncovering the universe's most profound secrets. We're about to dive into 30 theories about the universe's hidden structures, ideas so extraordinary they challenge everything we think we know about reality itself. What if I told you that the cosmos might be far stranger and more intricate than we ever imagined? That beyond the familiar realms of planets, stars, and galaxies, there could be entire dimensions folded into the fabric of space, cosmic threads weaving through existence, or even parallel universes brushing up against our own. These aren't just wild speculations, they're serious scientific concepts, born from the cutting edge of physics and cosmology, each one inviting us to reconsider our place in the grand scheme of things. This video is your invitation to explore these breathtaking ideas, to journey beyond the visible and into the realm of the extraordinary. Together, we'll uncover theories that speak to the very nature of reality, from cosmic strings and holographic principles to branes and hidden dimensions. It's a voyage into the unknown, one that promises to expand your mind and ignite your imagination. So settle in, open your curiosity, and let's begin this adventure into the hidden architecture of the universe. Our journey into the hidden structures of the universe begins with one of the most fascinating and elusive concepts ever proposed: cosmic strings. Picture the universe in its first fleeting moments of existence, a searingly hot and dense soup of energy and fundamental forces. As it expanded and cooled, it underwent dramatic phase transitions, much like steam condensing into water or water freezing into ice. And just as ice crystals can form cracks and fissures as they solidify, these cosmic transitions might have left behind incredibly thin, incredibly dense defects, frozen into the very fabric of spacetime itself. These are the cosmic strings. Imagine a crack in the cosmos, but one that is not a void. Instead, it's a filament of pure energy, a one-dimensional thread so massive that a single inch of it could weigh more than a mountain range. They are theoretical relics, topological defects, meaning their existence is tied to the fundamental geometry of the universe's fields. They're not made of matter as we know it. They are flaws in the structure of reality, remnants from a time when the laws of physics were settling into the form we recognize today. The most compelling aspect of cosmic strings isn't just their origin story, but their potential effects. Their immense mass would warp spacetime around them, creating profound gravitational fields. This means they could act as natural cosmic lenses, bending the light from distant galaxies and stars that pass behind them. Astronomers searching the skies might one day spot a strange, duplicate image of a galaxy, a telltale sign of a cosmic string's gravitational lensing at work. Some theories even suggest that these strings could have provided the initial gravitational seeds necessary for matter to clump together, eventually forming the vast web of galaxies we see today. In this way, these hypothetical cracks could be the universe's hidden scaffolding, the invisible architecture upon which everything we see was built. But if the idea of cosmic strings warps our perception of space, then our next theory completely shatters it. We now venture into one of the most radical and mind-bending concepts in all of physics, the holographic principle. This is the astonishing proposal that everything we see and experience in our three-dimensional universe, every star, every planet, every one of us might actually be a complex projection of information encoded on a distant, two-dimensional surface. Our reality, in its entirety, could be a cosmic hologram. This revolutionary idea didn't emerge from pure speculation, but from a deep and troubling paradox at the heart of black hole physics. When matter falls into a black hole, it seemingly vanishes, erased from our universe, but this creates a fundamental conflict with a cornerstone principle of quantum mechanics. Information can never be truly destroyed. This is the famous black hole information paradox, a problem that has perplexed physicists for decades. In the 1990s, physicists like Gerard T. Hooft and Leonard Susskind made a breathtaking leap. They considered the event horizon of a black hole the point of no return. They realized that the maximum amount of information this surface can contain is not proportional to its volume, as you might expect for a three-dimensional object, but to its surface area. The event horizon, a two-dimensional boundary, seemed to hold all the information about everything that had ever fallen inside. It was as if the three-dimensional interior of the black hole was being described, or projected, from the data painted on its two-dimensional surface. This revelation was the seed of the holographic principle, suggesting that this might not be a strange property unique to black holes, but a fundamental feature of our entire universe. Think of it like the hologram on your credit card. That shimmering, three-dimensional image isn't actually deep. It is created from interference patterns etched onto a flat, two-dimensional plastic surface. In the same way, our universe, with its rich depth and volume, might be encoded on a vast, remote boundary we cannot see. Every event, every particle, every force we experience here could be the result of complex information processing happening on this lower dimensional surface at the edge of everything. The implications of this are staggering. It suggests that the world we perceive is not the primary reality, but a secondary projection. The true, fundamental laws of physics might be written in two dimensions, and our 3D world is simply how those laws manifest to us. This principle offers a potential solution to the information paradox, implying that information isn't lost in a black hole, but is instead smeared across its event horizon, preserved forever. It forces us to question the very nature of reality. Is the depth we perceive just an illusion? Are space and time themselves emergent properties, arising from a more basic, information-based framework? The holographic principle doesn't just add a new layer to our understanding. It suggests we might have been looking at the entire picture from the wrong dimension all along. To truly grasp the immense power of the holographic principle, we need to explore the specific mathematical framework that brought it from a fascinating analogy into a serious theoretical tool, a concept known as the anti-de Sitter/conformal field theory correspondence, or ADS/CFT for short. This is not just a vague idea. It is a precise, and in some cases proven, duality. It proposes a perfect equivalence between two seemingly completely different universes of physics. On one side, we have a universe that contains gravity, operating within a hypothetical shape known as anti-de Sitter space. On the other side, we have a universe without gravity at all, described by a quantum field theory living on the lower dimensional boundary of that first space. There are two utterly different descriptions of the same reality, like discovering that a detailed novel and a complex symphony are actually telling the exact same story. Let's break down this astonishing pair. Anti-de Sitter space, or ADS, is a particular solution to Einstein's equations of general relativity. Think of it as a universe with a negative curvature, a sort of saddle shape that bends away from itself. Crucially, this type of space has a very clear and definitive boundary at infinity. Now, on this boundary, physicists can define a conformal field theory, or CFT. This is a special type of quantum theory that lacks any fixed scale, meaning it looks the same at all levels of magnification, and most importantly, it has no gravity in its description. The sheer brilliance of ADS/CFT is the claim that these two theories are not just similar, they are completely equivalent, they are dual to one another. Every single process, every particle, every interaction that happens in the gravitational bulk of the ADS space has a perfect one-to-one counterpart in the non-gravitational quantum equations living on its flat boundary. A star collapsing into a black hole in the interior could be described as a specific thermalization process happening in the quantum soup on the edge. There are two languages describing the same event. This duality has earth-shattering implications for our understanding of gravity itself. For decades, the greatest challenge in fundamental physics has been reconciling Einstein's theory of gravity, which warps the stage of spacetime, with quantum mechanics, which governs the frenetic dancers upon it. They speak completely different mathematical languages, but AD/CFT offers a breathtaking new perspective. Gravity might not be a fundamental force at all. Instead, it could be an emergent phenomenon, a collective illusion that arises from the complex quantum interactions of countless tiny degrees of freedom on a lower dimensional surface. In this view, gravity is a thermodynamic force, much like how the pressure of a gas isn't a fundamental property of any single atom, but emerges from the statistical behavior of trillions of them. The force that holds planets in orbit and bends starlight could be a direct consequence of quantum information processing happening at the very edge of the universe. This perspective provides a powerful new way to tackle some of the most intractable problems in physics, particularly the black hole information paradox. If a black hole's interior is holographically encoded on its event horizon, then information never actually falls in and is never truly lost. It is simply transformed and stored in an incredibly complex, scrambled state on the surface. The paradox vanishes when you accept that the true description of the black hole isn't the dark, mysterious interior, but the vibrant, information-rich quantum theory on its boundary. The holographic principle, through AD/CFT, suggests that information is the most fundamental currency of the universe, and everything else, including the force of gravity and the very dimensions of space and time, is built from it. We are not living in a universe with gravity. We are living in a holographic projection of a universe where information behaves in such a way that it creates the illusion of gravity for us. If the holographic principle suggests our universe might be a projection, then brane cosmology proposes something even more tangible, that our entire cosmos is just one slice of a much larger, higher dimensional reality. This theory emerges from the depths of string theory, and to understand it, we need to shift our perspective in a truly radical way. We are all intimately familiar with our four-dimensional world, three of space and one of time. But what if those are not the only dimensions that exist? Imagine, for a moment, that reality has many more spatial dimensions, perhaps 10 or 11 in total, all curled up or extended in ways we cannot perceive. In this grander arena, our universe might not be all there is. Instead, it could be a three-dimensional membrane, or brane for short, floating within a higher dimensional space known as the bulk. Think of it like this. A single page of a book exists in three dimensions. It has length, width, and a tiny, almost negligible thickness. To tiny beings living entirely on the flat surface of that page, their entire reality would be two-dimensional. They could move left and right, forward and backward, but the concept of up or down off the page would be incomprehensible to them. They would be completely unaware of the other pages in the book, all existing in the same three-dimensional space around them. In this analogy, our universe is that page, a three-dimensional brane, and the bulk is the entire book, the higher dimensional space that contains countless other branes, each potentially hosting their own separate universes with their own unique laws of physics. This elegant idea provides a stunningly simple and powerful explanation for one of the most persistent mysteries in physics. Why is gravity so unimaginably weak compared to the other fundamental forces? Consider the magnet on your fridge. That tiny magnet, using the electromagnetic force, can overcome the gravitational pull of the entire Earth trying to pull it down. Gravity is weaker by a factor of 1 followed by 36 zeros. This is known as the hierarchy problem, and it has baffled scientists for generations. Brane cosmology offers a beautiful solution. The proposal is that while the strong and weak nuclear forces and electromagnetism are bound to our brain, operating only within our 3 spatial dimensions, gravity is different. It is the result of vibrations in the fabric of spacetime itself, and as such, it can leak. It can propagate into the extra dimensions of the bulk. This leakage dilutes gravity's strength. From our perspective, trapped on our brain, gravity seems weak because its true force is spreading out into these unseen dimensions. Imagine a sound wave in a large, open field. It spreads out in all directions and becomes faint very quickly. But if that same sound wave was confined to a narrow hallway, it would remain strong and intense over a much greater distance. Gravity is like that sound wave in the open field of the bulk, while the other forces are like sound waves trapped in the narrow hallway of our brain. We only experience a tiny fraction of gravity's full intensity because most of it is flowing into realms we cannot access. The implications of this are truly cosmic. If other branes exist in the bulk, they could be drifting incredibly close to our own, separated by a gap smaller than an atom, yet completely undetectable because all the matter and forces we're made of are stuck to our own brain. We could have an entire parallel universe just a millimeter away in a higher dimension, and we would never see it or touch it. The only way we might sense its presence is through gravity, the one force that can bridge the gap between branes. Some theories even suggest that a catastrophic collision between 2 branes moving in the bulk could have been the event that triggered our own Big Bang, setting our entire universe into motion. This transforms the cosmos from a solitary existence into a potentially crowded multiverse, a vast higher dimensional ocean dotted with island universes, each with its own unique story. This extraordinary vision of a multiverse of floating branes leads us directly to our 5th theory, one of the most compelling and elegant alternatives to the classic Big Bang, the ekpyrotic universe model. The name itself comes from the ancient Greek word for conflagration or out of fire, and it paints a dramatic picture of our cosmic origins, not as a singular explosion from nothingness, but as a colossal collision between 2 of these primordial membranes. Imagine 2 immense, flat, and perfectly parallel sheets of reality, drifting silently through the higher dimensional bulk. They are drawn together slowly, almost inevitably, by the gravitational force that bleeds between them. Their approach is not a head-on crash, but a gentle, glancing blow, a cosmic scrape of unimaginable power. This contact, this moment of brain collision, is what we experience as the Big Bang. The immense energy of that impact is converted into the searing heat and the dense soup of matter and radiation that filled the nascent universe, setting the entire cosmic story in motion. But the ekpyrotic model offers something even more profound than a new creation story. It proposes a cyclic universe, an eternal rhythm of birth, death, and rebirth. After the fiery collision, the 2 branes bounce apart, repelled by the very forces that brought them together. Our universe, born on one of these branes, then begins its long evolution. It expands, cools, galaxies form, stars live and die, and eventually, over trillions of years, it becomes a cold, dark, and dilute emptiness, destined for a heat death. Yet, this is not the end. Across the vast gulf of the bulk, the other brane is still there. The subtle gravitational attraction between them never truly vanishes. Over an almost unimaginable timescale, the branes are pulled together once more, culminating in another universe-forming collision. This cycle of collision, expansion, and contraction could, in principle, repeat forever, an eternal cosmic heartbeat with no beginning and no end. One of the model's greatest strengths is its elegant solution to a problem that inflation was designed to fix. the stunning uniformity of our universe. When we look at the cosmic microwave background radiation, the ancient afterglow of the Big Bang, we see that it is almost perfectly smooth, with temperatures uniform to within tiny fractions of a degree across the entire sky. For the universe to be this homogeneous, all regions must have been in thermal contact early on, but in the standard Big Bang model, these regions were moving away from each other too quickly for light or heat to ever have connected them. Cosmic inflation solves this by positing a period of faster-than-light expansion that stretched a tiny, uniform patch into our entire observable cosmos. The ekpyrotic model, however, achieves this uniformity through a different and perhaps more natural mechanism. Because the pre-collision branes are flat, infinite, and parallel, they are inherently uniform. The energy released when they collide is therefore smooth, and even across their entire vast surface. The Big Bang, in this view, didn't start from a chaotic, singular point. It was ignited across a vast, pre-existing, and uniform canvas, neatly explaining the smoothness we observe without needing a separate inflationary epoch. Like any bold theory, the ekpyrotic model makes specific predictions that astronomers can search for. It suggests that the primordial gravitational waves, ripples in spacetime from the universe's violent birth, would be much weaker than those predicted by most inflationary models. The initial brane collision is a much gentler, more ordered process than the chaotic energy fields that drive inflation. So far, observations have not detected the strong primordial gravitational wave signal that would be a hallmark of many inflationary theories, a result that is more consistent with the ekpyrotic scenario. However, the model also faces significant challenges. The physics of the bulk and the precise nature of the brane collisions involve speculative string theory concepts that are difficult to test directly. Furthermore, ensuring the cycles can continue indefinitely without eventually dissipating or building up entropy from one cycle to the next requires some delicate theoretical footwork. While it remains a respected and active area of research for a group of theoretical cosmologists, it is currently considered a more speculative alternative to the inflationary paradigm, which has a broader base of support and a wider range of models that align with existing data. Yet, its power to reframe our cosmic beginning as part of an endless cycle offers a profoundly different and intellectually thrilling perspective on the ultimate fate of all things. If the idea of a cyclic cosmos of colliding branes expands our view of time, then the concept of the inflationary multiverse does something even more profound. It suggests our entire universe might be just one bubble in an endless, frothing cosmic sea. This breathtaking theory emerges from the most successful idea in modern cosmology, cosmic inflation, and follows its logic to a staggering conclusion. Inflation proposes that a fraction of a second after the Big Bang, the universe underwent a period of hyper-fast, exponential expansion, smoothing it out and planting the seeds for all future structure. But what if this inflationary period didn't have a clean, universal end? What if, in some regions, it just never stops? This is the core of eternal inflation. Imagine the driving force behind inflation as a kind of quantum field, often visualized as a ball rolling down a hill into a valley. The valley represents the stable, low-energy state of our current universe, the true vacuum. The hill represents the high-energy, unstable false vacuum that powered inflation. In most versions of the story, the ball rolls down everywhere at once, ending inflation and converting that false vacuum energy into the hot plasma of the Big Bang. But quantum mechanics introduces a fascinating wrinkle. At the tiniest scales, there are always random fluctuations. So while the ball might roll down the hill in most places, in some rare, random patches, a quantum fluctuation could actually kick the ball back up the hill. In these regions, the high-energy false vacuum state persists, and with it, the furious exponential expansion of space continues unabated. Now, here's where it gets truly mind-bending. In these regions where inflation continues, space is expanding so much faster than in the areas where it has stopped. This means the still inflating false vacuum rapidly dominates the overall volume of the multiverse. It becomes an endless, ever-expanding background ocean. Meanwhile, in the spots where the ball finally rolled down into the valley, where inflation ended, that energy was released, creating a hot, dense, expanding bubble of a universe like our own. But this bubble is now surrounded by the rapidly expanding false vacuum ocean. Each of these bubbles is completely causally disconnected from the others. The space between them is expanding faster than light can ever hope to cross it, making them forever isolated islands of reality. The process that creates each bubble is known as false vacuum decay, a concept that is both elegant and terrifying. It's a quantum tunneling event where a tiny region of space spontaneously and randomly transitions from the high-energy false vacuum to the low-energy true vacuum. This is not a slow process. Once a bubble nucleates, it expands outward at nearly the speed of light. The wall of this expanding bubble is a ferocious wave of energy release, and inside it, a new universe with stable physical laws is born. And this isn't a one-time event. In the eternally inflating background sea, this process is happening everywhere, all the time, an endless chain reaction of cosmic nucleation, spawning an infinite number of separate bubble universes. This leads to the most profound implication of the theory. The physics inside each bubble can be different. When a bubble forms, the way the inflationary field settles into its stable state can vary, a process known as spontaneous symmetry breaking. This settling determines the fundamental constants of nature within that bubble: the strength of gravity, the mass of an electron, the number of spatial dimensions. In our bubble, these constants are perfectly tuned for the emergence of atoms, stars, planets, and life, but in others, they could be wildly different. Some universes might have gravity so strong they instantly collapse back into a black hole. Others might have forces too weak for atoms to ever form, forever remaining a barren soup of elementary particles. We live in a universe that is habitable, not because it is special, but because it is one of countless variations in an infinite multiverse where, statistically, a few will inevitably have the right conditions for life. This is the ultimate answer to the fine-tuning problem, suggesting that the seemingly miraculous constants we observe are not miracles at all, but simply our local bylaws in a vast cosmic federation where every possible law exists somewhere. While this idea is a powerful and logical extension of our best cosmological models, it remains, by its very nature, incredibly difficult to test. By definition, these other bubble universes are beyond our observable horizon, separated from us by an expanse of inflating space that light can never traverse. Some theorists have speculated that if another bubble universe were to nucleate very close to our own in the higher dimensional bulk and then expand, we might one day see its approach as a strange, circular disturbance in the cosmic microwave background, or even witness a catastrophic collision as its high-energy wall eventually contacts our universe. But such an event would likely be unsurvivable and is considered extremely improbable. For now, the inflationary multiverse remains a spectacular and compelling theoretical prediction, a vision of reality so vast and diverse that it challenges our very understanding of what existence means, suggesting that all that can happen does happen in a cosmos without end. This breathtaking vision of an infinite multiverse of bubbles, each with its own unique physics, challenges our sense of uniqueness. But what if the ultimate hidden structure isn't out there in some distant cosmic sea, but is being generated right here, right now, with every single decision the universe makes? This brings us to one of the most debated and extraordinary ideas in all of science. the many worlds interpretation of quantum mechanics. To understand this, we first need to grapple with the central weirdness of the quantum world, a problem known as the measurement problem. In our everyday experience, objects have definite properties. A car is either in the garage or it isn't. But in the quantum realm, particles like electrons exist in a fuzzy state of superposition. An electron isn't definitively here or there. It exists as a cloud of probability, a blend of all its possible positions and states at once. This is described by its wave function. The bizarre part comes when we try to measure it. The instant we observe the electron, this cloud of possibilities seems to collapse, instantly snapping into a single, definite reality. The question that has haunted physicists for a century is, what exactly causes this collapse, and why does the act of observation have such a special, privileged role in shaping reality? In 1957, a young PhD student named Hugh Everett proposed a radical and elegant solution. He suggested that the wave function never actually collapses. There is no special magic moment of observation. Instead, he took the mathematics of quantum mechanics at complete face value. Everett proposed that every single time a quantum system faces a probabilistic outcome, the entire universe branches. All possibilities are realized, but each one plays out in its own newly created, parallel world. In this view, the universe is a constantly flowering tree of reality, where every fork in the quantum road is taken, creating a vast, ever-growing multiverse of parallel timelines. Let's make this concrete with the famous thought experiment of Schrödinger's cat. In the standard interpretation, the cat in the box is both alive and dead, a superposition, until someone opens the box and collapses the wave function, revealing one outcome. But according to many worlds, there is no superposition of a half-dead, half-alive cat. Instead, at the moment the radioactive atom either decays or doesn't, the universe splits in two. In one branch, the atom decayed, the poison was released, and the cat is dead. In the other, equally real branch, the atom did not decay, and the cat is alive and well. Both outcomes happen 100%. There is no collapse. There is only addition. The person who opens the box also splits. One version of them sees a dead cat and feels grief. The other version sees a living cat and feels relief. Both experiences are completely real, but they are now forever separated, living in parallel worlds that can no longer interact. This interpretation paints a picture of a hidden structure of reality that is almost beyond comprehension. It suggests that right now, an astronomical number of branching events are occurring every second, from the decay of atoms to the firing of neurons in your brain. For every quantum event with even two possible outcomes, the cosmos divides. This creates a multiverse of staggering proportions, where every possible history and every possible future actually exists. There is a world where you turned left instead of right this morning, a world where the dinosaurs never went extinct, and a world where every single quantum coin toss throughout history went the other way. This isn't just about different choices, it's about every single quantum possibility, no matter how small, spawning a new, full-fledged universe. It is crucial to address some of the most common misconceptions about this theory. First, these branches are not separate places in our space. They are entirely separate universes within a larger multiverse. You cannot travel to them because they are not elsewhere. They are a different reality altogether. Second, the branching is not a conscious choice or something you can feel. Your conscious experience simply follows one branch of the wave function. You are only aware of the single timeline you are in, completely oblivious to the countless other versions of you experiencing every other possibility. And finally, this is not science fiction. It is a serious, and to some physicists, the most straightforward interpretation of the existing and wildly successful equations of quantum mechanics. It removes the need for an arbitrary and unexplained collapse rule. offering a picture of reality that is, in its own way, simpler and more complete. The cost, of course, is accepting that we live in a reality of truly infinite possibilities, where every story that can be told is being told somewhere in the hidden architecture of the quantum multiverse. This journey through parallel quantum worlds leads us to a theory that is, in many ways, the ultimate abstraction. If the many worlds interpretation suggests that every quantum possibility is realized, then the mathematical universe hypothesis asks a far more fundamental question: what is the substance of those realities? Proposed by the physicist and cosmologist Max Tegmark, this hypothesis presents a staggering and beautifully minimalist answer. It posits that our physical reality is not just described by mathematics, it is mathematics. More than that, it argues that every self-consistent mathematical structure doesn't just describe a possible universe, it actually is a universe, existing in its own right within a multiverse of ultimate logic. To grasp the sheer force of this idea, we need to consider the uncanny effectiveness of mathematics. Why is it that the universe seems to follow mathematical rules with such impeccable precision? We can write down an equation like E=mc squared on a piece of paper, and it correctly predicts the energy released by a star millions of light years away. We can use abstract mathematical concepts like imaginary numbers and Hilbert spaces to design the circuitry in the device you're using right now. It works with a reliability that feels almost miraculous. The traditional view is that we invent mathematics as a language to describe the physical world we discover. Tegmark turns this completely on its head. He suggests that we are not inventing mathematics, we are discovering it, and the physical world we perceive is just a particular manifestation of a much deeper, abstract mathematical reality. Think of it like this. Imagine a perfect circle. It is an abstract mathematical object defined by the set of all points that are equidistant from a single center. You can never draw a perfect circle in the physical world. The best you can do is a physical approximation of the ideal Platonic form. The mathematical universe hypothesis proposes that the perfect abstract circle exists in a realm of mathematical reality. Now, extend that idea to everything. The laws of physics, the particles, the forces, they are not the primary reality. They are simply a shadow, a particular representation of an underlying, immutable mathematical structure. In this view, an electron isn't a tiny ball of matter. It is an excitation in a particular field, which is itself just a specific solution to a set of differential equations. The universe is not running like a computer program. It is the program. The physicality we experience is simply how that mathematical structure feels from the inside. This leads to the hypothesis's most profound and dizzying implication, the level 4 multiverse. Tegmark categorizes multiverses into 4 levels. Level 1 is the infinite space beyond our horizon, containing regions with identical laws but different initial conditions. Level 2 is the inflationary bubble multiverse, with different physical constants. Level 3 is the quantum many worlds branching universe, but level 4 is the ultimate, all-encompassing ensemble. It states that all mathematical structures exist physically. Every universe that can be described by a self-consistent set of mathematical equations is real. This includes universes governed by the familiar laws of Einstein and Schrödinger, but it also includes universes with entirely different dimensions, with forces we cannot conceive of, with logic that operates differently from our own. There is a universe described by the laws of classical mechanics with no quantum weirdness. There is a universe that is, in its entirety, a perfect, empty dodecahedron. If a structure can be defined without logical contradiction, it exists somewhere in the level 4 multiverse. This idea provides a spectacular and final answer to the question of why our universe seems so finely tuned for life. It is not fine-tuned at all. We simply find ourselves in one of the vast, but perhaps uncommon mathematical structures that contain self-aware subsystems, what we call conscious observers capable of pondering their own existence. In the unimaginably vast landscape of all mathematical possibilities, most structures are likely barren, chaotic, or transient. We could not exist in a universe whose mathematical laws do not allow for the formation of stable atoms, complex molecules, or the flow of time. Our presence selects out the tiny subset of mathematical universes that are compatible with life. This is known as the anthropic principle, applied to the ultimate degree. Of course, such a radical theory faces significant criticisms and challenges. The most pointed question is, what does it mean for a mathematical structure to exist? Does the number 7 exist in the same way that a rock does? Tegmark would argue that the difference is merely perceptual. Another major challenge is that of testability. How could we ever gather evidence for the existence of a universe based on a completely different mathematical foundation, one with which we could never interact? Some suggest that if our universe is indeed a mathematical structure, there might be observable glitches or computability constraints in its fabric. Furthermore, the hypothesis struggles with the concept of consciousness, forcing us to ask how a self-aware perception of reality, a feeling, a thought can emerge from a cold, impersonal equation. Despite these profound questions, the mathematical universe hypothesis remains a powerful and compelling endpoint for a quest to understand reality's foundation. It pushes the idea of a hidden cosmic structure to its logical extreme, suggesting that at the very bottom of everything, beneath the quantum fields and the forces of nature, there is only mathematics, eternal and immutable, with our vibrant, complex universe being just one beautiful example in an infinite library of logical possibilities. The mathematical universe hypothesis, while breathtaking in its scope, forces us to confront some of the most profound philosophical questions imaginable. The first is the puzzle of consciousness itself. If our universe is ultimately just an abstract mathematical structure, how does that cold, impersonal framework give rise to the warm, vivid, subjective experience of being? How do sets of equations produce the feeling of wonder when gazing at the stars, the ache of sadness, or the color red? This is the famous hard problem of consciousness, and the MUH doesn't solve it so much as recast it in a new light. It suggests that consciousness might not be a physical process emerging from brain chemistry alone, but could instead be a fundamental property of certain types of sufficiently complex, self-modeling mathematical structures. In this view, your conscious experience isn't generated by the math. It is an intrinsic aspect of that particular mathematical pattern being instantiated. You are not a ghost in the machine. You are the machine, and the machine is math. This perspective aligns with some forms of pancomputationalism, the idea that the universe is fundamentally computational, and that consciousness is a type of information processing. This leads directly to the unreasonable effectiveness of mathematics in the natural sciences, a phrase coined by physicist Eugene Wigner. Why does math work so shockingly well? We can develop a branch of pure mathematics based on nothing but abstract logic and aesthetics, and decades later physicists discover it perfectly describes the behavior of subatomic particles. Wigner found this to be a mysterious gift we neither deserve nor understand. The MUH flips this mystery on its head. Mathematics isn't effective at describing the universe. The universe is mathematics. The reason a physicist's equations match experimental results is because both the experiment and the equations are different expressions of the same underlying mathematical structure. There is no mystery of effectiveness because there is no separation between the description and the thing being described. They are one and the same. However, For all its elegant explanatory power, the MUH faces significant and robust criticisms. The most glaring is the measure problem. If every possible mathematical structure exists, then the number of universes that are chaotic, unstable, or just incredibly boring vastly outnumbers those that can support complex life. There are infinitely many mathematical structures that are just empty, or that contain nothing but a single number, or that are entirely random and unstructured. So why do we find ourselves in a universe with such beautiful, orderly, and complex laws? The anthropic principle is invoked. We can only observe a universe compatible with our existence, but in an infinite sea of possibilities. How do we even define probability? Without a way to count or weigh these different structures, it becomes difficult to say that an ordered universe like ours is in any way likely or natural. It simply is. A second major criticism targets the very definition of a mathematical structure. The hypothesis hinges on these structures being self-consistent, but is that enough? Some mathematical structures might be consistent, but utterly trivial or devoid of any interesting properties. Does the equation 1 = 1 constitute a universe? If so, what does it contain? Furthermore, the hypothesis struggles with the nature of existence itself. What does it mean for a mathematical structure to exist in a physical sense? Proponents argue that abstract existence is the only kind of existence. The number 4 doesn't need a physical body to be a real concept, but critics counter that this is a philosophical sleight of hand, conflating the map with the territory. Finally, the theory is often accused of being untestable and therefore unscientific, since we are, by definition, trapped within our own mathematical structure. How could we ever gather evidence for the existence of others? Any observation we make will necessarily be consistent with our own local mathematical laws. We cannot peek outside the system to see what other systems might be there. Some have speculated that if our universe is a mathematical structure being computed, we might find evidence of computability limits or digital glitches in the fabric of reality, but such ideas remain highly speculative. Despite these formidable challenges, the mathematical universe hypothesis endures because it represents the ultimate endpoint of a quest for a final theory. It pushes reductionism to its absolute limit, suggesting that at the bedrock of reality, there is nothing left to reduce only timeless, immutable, and beautiful mathematics. Yet for all its grandeur, the idea of a mathematical multiverse operates on a scale almost too vast to comprehend. It suggests that reality's deepest layers are not physical, but logical. But what if we could find evidence of a truly physical structure, a cosmic neighbor of immense proportions, lurking just beyond the veil of our observable universe? This brings us to a chilling and compelling mystery rooted not in abstract equations, but in the direct, observed motion of galaxies themselves. Astronomers have given it a name that sounds like it's straight out of science fiction: dark flow. To understand dark flow, we need to first picture the standard model of cosmic expansion. After the Big Bang, the universe began to fly apart, and it continues to do so. We measure this through the redshift of distant galaxies. The farther away a galaxy is, the faster it appears to be receding from us. This motion is smooth and uniform in all directions, like dots on an inflating balloon. This is the Hubble flow, the foundational backdrop of an expanding cosmos. On top of this, galaxies and even entire clusters have their own smaller, local motions, tugged this way and that by the gravitational pull of their neighbors, like eddies and currents in a great river. These are expected and well understood, but in the early 2000s, a team of astronomers led by Alexander Kashlinsky made an astonishing discovery while studying the cosmic microwave background, the afterglow of the Big Bang. They were using the CMB as the ultimate frame of reference, a fixed backdrop against which to measure the true peculiar velocities the local motions of large clusters of galaxies. What they found was not a random jostle. They detected a startling, coordinated drift. Hundreds of galaxy clusters, scattered across billions of light years, were all moving in the same direction at incredible speeds, over 2 million miles per hour. This wasn't part of the general expansion. This was a mysterious, coherent stream, as if some immense, unseen force was pulling them. They called this phenomenon dark flow, a name evoking the other great cosmic unknowns, dark matter and dark energy. The sheer scale of this motion is what makes it so perplexing. These clusters are so far apart that the gravitational influence of any known structure within our observable universe could not possibly coordinate their movement. The Great Attractor, a massive concentration of mass in the region of the Centaurus and Norma constellations, was once thought to be the source of our local galaxy's motion. But the Great Attractor's pull is local. It cannot account for a flow that spans a quarter of the visible sky. Dark flow implies a gravitational source so immense it defies explanation, and one that lies beyond our cosmological horizon. We are seeing the shadow of something we cannot see, a pull from a region of space from which light has not had time to reach us since the beginning of the universe. But this is where the theory ventures into truly speculative and thrilling territory. What could possibly exert such a titanic gravitational influence from outside our observable bubble? One extraordinary possibility is that dark flow is evidence of a pre-Big Bang structure, a vast unevenness in the primeval fabric of reality that survived inflation and is now tugging on the matter in our universe. Another, even more radical idea is that we are feeling the gravitational pull of another universe entirely. In the context of the inflationary multiverse we discussed earlier, our bubble universe might not be perfectly isolated. If another bubble universe formed relatively nearby in the greater multiversal bulk, its immense mass and energy could be gravitationally influencing the matter in our own universe, creating this coherent stream. We would be sensing the presence of a separate cosmos, an island universe in the wider multiverse, forever hidden from our view by the ultimate curtain of the cosmological horizon, but revealed by its relentless gravitational pull. Naturally, such a profound claim has been met with intense scrutiny and skepticism within the scientific community. Some researchers have questioned the methodology of the original studies, suggesting that the observed signal could be an artifact of incomplete data or calibration errors in the instruments used to map the CMB. Subsequent analyses have yielded conflicting results. Some have failed to detect the flow at all, while others have confirmed it and even suggested it extends to even greater distances. The Planck satellite, the most advanced mission to map the cosmic microwave background, did not find conclusive evidence for the dark flow as originally described, casting significant doubt on its existence for many cosmologists. The debate continues, highlighting the extraordinary difficulty of measuring such subtle effects at the very edge of the observable universe. Whether dark flow is ultimately confirmed or dismissed, its investigation represents a monumental effort to push the boundaries of cosmology. It challenges us to ask what could lie beyond the limits of our vision, and to consider that the greatest structures in existence might be those we can only infer from their ghostly pull on everything we can see. It is a tantalizing hint that our cosmic map is profoundly incomplete, and that the unknown doesn't end at the horizon of our observable universe. It may only just begin there. Yet if the idea of a mysterious flow of galaxies hints at an external pull, our next theory points to something far more fundamental and unsettling, a potential crack in the very cornerstone of modern cosmology. This is the controversial story of the so-called axis of evil, a name that perfectly captures the profound threat it poses to our understanding of the universe's basic symmetry. For centuries, A guiding principle of cosmology has been the cosmological principle, which states that on the largest scales, the universe is isotropic and homogeneous. Isotropy means it looks the same in every direction you look. Homogeneity means it has a uniform distribution of matter everywhere. This principle is the bedrock upon which almost all of our models are built, from the Big Bang to cosmic inflation. It's why we feel confident that the physics we discover in our little corner of the cosmos applies to the universe as a whole. This assumption of perfect isotropy was seemingly confirmed with stunning precision when we mapped the cosmic microwave background radiation. The CMB is the oldest light we can see, a snapshot of the infant universe when it was just 380,000 years old. That snapshot revealed a universe that was almost perfectly smooth, with temperature fluctuations of only about 1 part in 100,000. It was hailed as the ultimate proof of the cosmological principle, but as our instruments got better and we looked closer, a few stubborn, strange anomalies began to emerge. The most significant of these is a peculiar alignment of the largest temperature fluctuations that seems to define a preferred direction in space, an axis. Researchers half-jokingly gave this mysterious alignment its dramatic name, the axis of evil, because if true, it undermines the very idea of a random, isotropic universe. So what exactly are we seeing? When scientists analyze the CMB data, they break down the temperature map into components using a mathematical technique called multipole analysis. The dipole is the largest variation caused by our own motion relative to the CMB rest frame. The quadrupole and octupole represent the next largest patterns of hot and cold spots. The astonishing finding is that the planes of these quadrupole and octupole moments appear to be aligned with each other, and even more bizarrely, they are also aligned with the ecliptic plane of our own solar system and the direction of the CMB dipole. This is deeply strange. The largest patterns in the structure of the entire observable universe seem to be coordinated with the orientation of our local, insignificant solar system. It's as if the entire cosmos has a giant, invisible arrow painted on it, and that arrow is weirdly pointing in a direction that has special meaning for us. The probability of this happening by pure chance in an isotropic universe is incredibly low, suggesting that either we are at the center of some kind of cosmic structure, a return to a pre-Copernican nightmare, or there is a systematic error we haven't accounted for. Naturally, the scientific community has vigorously pursued the possibility of an error. Could this alignment be an artifact of our own galaxy? Perhaps dust or other foreground emissions are contaminating the signal. Meticulous work by teams using data from the WMAP and later the Planck satellite have subtracted out these foregrounds, and the anomaly persists. Could it be an instrumental effect or a problem with the data processing? Years of analysis have yet to find a smoking gun that fully explains it away. This persistent signal forces us to consider the truly radical possibility that it might be real, a genuine feature imprinted on the cosmos at its birth. If the axis of evil is a real cosmological feature and not a flaw in our data, then what kind of hidden structure could have caused it? One extraordinary theory suggests it could be the ghost of a pre-Big Bang geometry. The standard inflationary model wipes the slate clean, erasing any pre-existing structure and creating a smooth, isotropic universe. But what if inflation wasn't perfectly efficient? What if some aspect of the primordial geometry that existed before the Big Bang managed to survive the inflationary expansion? The alignment we see could be a fossil, a scar from a time before time, a remnant of a structure that imposed a preferred direction on the very fabric of spacetime as our universe was born. This would mean our cosmos is not entirely independent. Its form was shaped by a hidden architecture that predates it. Another mind-bending possibility involves the very nature of spacetime itself. Could the universe be finite and have a non-trivial topology? Imagine space is not infinite and flat, but curved and connected to itself in a complex way, like a video game where going off one edge of the map brings you back to the other side. If the universe had a small, donut-like torus shape or another complex topology, the light from the Big Bang could wrap around it, creating repeating patterns and large-scale correlations that appear as alignments to an observer inside it. We would be seeing the same structure from multiple different directions, creating the illusion of a preferred axis. The axis of evil, in this view, wouldn't be an axis at all, but a glimpse of the global shape of our entire finite universe, a shape we are inside of and cannot easily see. The debate over the axis of evil remains one of the most intriguing and unresolved in cosmology. Many scientists still lean towards it being a complex statistical fluke or a subtle systematic error we have yet to uncover. Its significance is still hotly debated, and it has not been universally accepted as a genuine violation of isotropy. However, its persistence challenges us to remain open to the extraordinary. It is a tantalizing clue that the universe might not be as random and featureless as we supposed, and that its deepest secrets might be written not just in the tiny fluctuations of the CMB, but in their unexpected and strangely coordinated alignment. But if the axis of evil hints at a universe with a hidden shape, then our next theory proposes a cosmos with a hidden rhythm and endless, eternal heartbeat. This is the captivating idea of the Big Bounce and other cyclic models, which completely reimagine the very beginning of our universe. Instead of a single, explosive birth from nothingness, these theories suggest we are living in just one cycle of an infinite series, with each Big Bang actually being a big bounce from a prior universe's collapse. This concept finds a powerful and rigorous voice in the field of loop quantum cosmology, a branch of physics that applies the principles of loop quantum gravity to the universe as a whole. In the standard Big Bang model, if you rewind the cosmic film, everything converges to a single point of infinite density and temperature, a singularity. Singularities are where our known laws of physics break down completely. They are essentially gaps in our understanding, screaming for a more complete theory. Loop quantum cosmology provides exactly that. It proposes that the fabric of spacetime is not smooth and continuous, but is instead woven from tiny, finite loops, a granular structure at the smallest possible scale, known as the Planck length. This quantum graininess has a profound consequence. It prevents matter and energy from being compressed into an infinitely dense point. Imagine squeezing a spring. You can compress it, but there's a limit. Eventually, it will push back with tremendous force. In loop quantum cosmology, spacetime itself acts like that spring. As a previous universe contracts under its own gravity, heading towards what would classically be a big crunch, it reaches a point of maximum possible density. The repulsive force generated by the quantum geometry of spacetime becomes overwhelmingly powerful, stopping the collapse in its tracks and causing the universe to rebound outward in a massive, hot expansion, a big bounce. What we experience as the Big Bang was not the absolute beginning, but simply the latest turning point in an endless cosmic cycle of contraction and expansion. This vision of a cyclic universe implies a breathtaking hidden temporal structure. Time, in this model, did not begin 14 billion years ago. It stretches back into the infinite past and will continue into the infinite future. Each cycle might last for trillions of years, encompassing a vast period of expansion, a slow coasting, and an eventual gravitational drawback together. Our entire cosmic history, from the first stars to the last black holes, is just one chapter in an epic with no first page and no final sentence. This elegantly avoids the philosophically troubling question of what happened before the Big Bang. There was no before in a linear sense, only a previous phase of the eternal cycle. The implications for the hidden structure of reality are profound. Information, for instance, might not be lost between cycles. While the universe is scrambled during the bounce, its particles and energy broken down and remixed, some theorists suggest that the quantum state of the previous universe could, in principle, imprint itself on the next one, creating a subtle cosmological inheritance. Furthermore, this model can naturally explain the smoothness and flatness of our universe without requiring a separate inflationary epoch. The intense, chaotic dynamics of the bounce itself could have the effect of ironing out any wrinkles and curvature from the previous cycle, setting the stage for the orderly expansion we observe today. We are not the product of a single, miraculous beginning, but the latest iteration in an eternal process of cosmic renewal, where the end of one story is merely the prologue to the next. While the Big Bounce offers a compelling vision of a cyclical universe rebounding from a quantum spring, another Nobel laureate has proposed a cycle of an entirely different character, one that doesn't end with a crunch, but with an eerie, endless expansion into a state of profound simplicity. This is Roger Penrose's conformal cyclic cosmology, a theory as beautiful and complex as the mind that conceived it. Penrose's model suggests that the universe doesn't bounce in a conventional sense. Instead, it undergoes a breathtaking metamorphosis, where the infinite future of one cosmic age seamlessly becomes the hot, dense beginning of the next. To understand this incredible transformation, we need to grasp two key ideas. The first is the far future fate of our universe. In the Standard Model, after trillions upon trillions of years, all stars will have burned out, black holes will have evaporated via Hawking radiation, and the universe will be a cold, dark, and nearly empty void, populated only by a sparse sea of diluted particles and radiation. This is the heat death, a state of maximum entropy where nothing ever happens. Penrose, however, saw a unique opportunity in this bleak finale. In this state, the universe loses all sense of scale. There are no massive objects left to define a meter, no energetic events to mark a second, with no particles with mass and only featureless radiation remaining. The concepts of distance and time become meaningless. The universe becomes effectively timeless and scale-less. This is where the second key idea, conformal rescaling, comes into play. Conformal geometry is a branch of mathematics that deals with angles but not distances. You can stretch or shrink a map, and as long as the angles between intersecting lines remain the same, its conformal structure is preserved. Think of a simple Mercator map of the world. It distorts the size of landmasses terribly, but the angles between lines of longitude and latitude are preserved, which is why it's still useful for navigation. Penrose proposed that we can perform a similar mathematical rescaling on the entire universe. At the end of time, we can mathematically shrink the vast, cold, empty universe down to a point, and its conformal geometry, its essential shape in terms of angles, would be identical to the hot, dense, small universe of the Big Bang. In this radical view, the heat death is not an end, but a conformal bridge. The remote future of one eon or cosmic cycle becomes the Big Bang singularity of the next. The universe forgets its scale and is reborn. The implications are staggering. There was no first universe, and there will be no last. We are living in one eon in an infinite chain, each beginning with a hot Big Bang and ending in a cold, empty void that becomes the next Big Bang. Time itself is cyclical, but not in a repetitive way. Each eon could have entirely different physical constants, particle content, and even dimensionality, as that information is lost in the conformal reset at the end of each cycle. Our entire cosmic history is just one iteration in an infinite sequence, but a theory this profound needs evidence, and Penrose, along with colleagues, has been searching for it in the oldest light we can see, the cosmic microwave background. If a previous eon existed, could it have left faint imprints on our own? Penrose believes so. His focus has been on the evaporation of supermassive black holes. In the previous eon, these monsters would have eventually evaporated in a final burst of energy via Hawking radiation. This release of energy, Penrose argues, would have been a violent, point-like event, and its trace could have been imprinted onto the conformal boundary that connects the eons, subsequently written into the fabric of our own early universe as it formed. These proposed imprints are known as Hawking points. They would appear in the CMB as faint, circular rings of slightly raised temperature, the ghostly signatures of the last gasps of giant black holes from a universe that existed before our own. The search for these points has been contentious. Penrose and his collaborators have published papers claiming to have found statistically significant evidence for these anomalous warm circles in the Planck satellite data. They argue that the distribution and nature of these spots are unlikely to be random fluctuations and are best explained by teases. However, the broader cosmological community remains deeply skeptical. Many scientists argue that the methods used to identify these points could be finding patterns in the random noise that is inherent in the CMB data. The human brain is exceptionally good at finding patterns, even where none exist, a phenomenon known as apophenia. Critiques have suggested that when more standard statistical techniques are applied, the evidence for Hawking points vanishes. Furthermore, some of the foundational aspects of teases, such as the assumption that all particles will eventually lose their mass, conflict with the standard model of particle physics, which posits that electrons, for example, are stable and will never decay. Despite the controversy, conformal cyclic cosmology remains a brilliant and captivating thought experiment. It challenges us to reconsider the very nature of beginnings and endings, proposing that they are one and the same, connected by a beautiful mathematical symmetry. It pushes the boundaries of cosmology to ask not just what happened at our Big Bang, but what could have happened before it, offering a poetic and infinite vision of a universe perpetually renewing itself through the elegant laws of geometry. This idea that our universe could be a link in an infinite cosmic chain inevitably leads us to a theory that offers a startlingly specific mechanism for this very process. It's a concept that transforms the most destructive objects in the cosmos into the ultimate cradles of creation. This is the black hole universe hypothesis, a mind-bending proposal that our entire cosmos, from its smallest particle to its largest galaxy, might exist within the interior of a black hole belonging to a much larger parent universe. To grasp this, we need to re-examine what happens during the formation of a standard black hole. When a massive star exhausts its nuclear fuel, its core collapses under its own immense gravity. This collapse is catastrophic and unstoppable, crushing matter down to a point of theoretically infinite density, a singularity. Around this singularity, an event horizon forms, a boundary beyond which nothing, not even light, can escape. From the perspective of the outside parent universe, an object that crosses this horizon is lost forever, its information seemingly trapped at the singularity. But the black hole universe hypothesis asks a radical question. What if that's not the end of the story? What if, from the perspective of something falling inside, the story is just beginning? The hypothesis suggests that the interior of a black hole is not a place of simple destruction, but a region where the laws of physics are reborn. When matter and energy collapse into a singularity, the conditions become so extreme that they might trigger a new inflationary Big Bang, birthing an entirely new universe with its own spacetime, physical constants, and dimensions. In this view, the singularity of a black hole in the parent universe is not a dead end. It is the white-hot spark of genesis for a separate infant cosmos. Our own Big Bang, then, might not have been a unique event in a void, but the natural consequence of a stellar collapse in a grander meta-universe, This leads to a truly fractal-like vision of reality, a cosmic matryoshka doll of unimaginable proportions. Every black hole that forms in our universe could, in turn, be the seed for a completely new universe within it. And within that daughter universe, the same process would repeat. Stars would form, live, die, and collapse into black holes, each one potentially spawning its own new cosmos. This creates an infinite, branching tree of universes, each nested within the black hole of a larger one. We could be living inside a black hole that exists in a universe, which is itself inside a black hole, in a sequence that stretches back forever. There is no ultimate top-level universe or final basement reality, just an endless recursion of creation within destruction. But how could the physics possibly work? How does the collapse of a star in one universe inflate into an entire cosmos? The key may lie in a radical reinterpretation of the singularity. In the Standard Model, the singularity is where general relativity breaks down, a sign that we need a theory of quantum gravity to understand it. Some quantum gravity models, like loop quantum gravity, suggest that a repulsive force generated by quantum effects could halt the complete collapse, causing a bounce, much like the one in cyclic models. This bounce, confined within the event horizon, would release an enormous amount of energy, initiating a rapid, inflationary expansion, a new Big Bang contained within the shell of the black hole's horizon. The implications for the hidden structure of reality are profound. First, it offers a potential explanation for why the fundamental constants of our universe seem so finely tuned for life. If new universes are born from black holes, then there could be a form of cosmic natural selection at play, universes that have physical constants which favor the prolific formation of black holes would produce more offspring. Over countless generations, the multiverse would become dominated by universes, like our own, that are exceptionally good at making stars that collapse into black holes. The laws of physics we observe wouldn't be a random accident. They would be the result of a Darwinian process on a cosmological scale, selected for their ability to perpetuate the cycle of creation. Furthermore, this hypothesis provides a fascinating new perspective on the event horizon. From the outside, the horizon is a point of no return, but from the inside, it might form the ultimate cosmic boundary, the edge of our observable universe, and the beginning of something else entirely. The cosmic microwave background radiation we study could be the redshifted and transformed afterglow of the fiery energy release from our parent black hole's formation. We are not looking back at the beginning of everything, but at the walls of our cosmic womb. Naturally, this is a highly speculative idea that currently sits at the far edge of theoretical cosmology. The greatest challenge is the sheer impossibility of testing it directly. By definition, we cannot send a probe outside our universe to check if we are inside a black hole, nor can we peer into a black hole in our universe to watch a new one being born. Any information about the parent universe is likely forever trapped beyond our cosmological horizon. However, some physicists suggest that if this model is correct, the initial conditions of our universe might carry a faint imprint, a specific signature in the distribution of the cosmic microwave background or the large-scale structure of galaxies that could one day be detected. For now, the black hole universe hypothesis remains a powerful and poetic thought experiment, one that elegantly merges the life cycle of stars with the origin of cosmos, suggesting that within the darkest tombs of the universe, new worlds are constantly being born. If a black hole is a cosmic drain from which nothing can escape, then a white hole would be its ultimate opposite, a celestial fountain from which nothing can enter. This is the captivating theory of white holes, the hypothetical time-reversed twins of black holes, and they might just be the universe's most profound, forbidden exits. To understand a white hole, we need to look at the mathematics of Einstein's theory of general relativity. the equations that describe a black hole are symmetric with respect to time. This means that if you were to take the mathematical solution for a black hole and literally reverse the direction of time in the equations, you would get a new, valid solution. This new object is a white hole, where a black hole's event horizon is a one-way street inward. A white hole's horizon is a one-way street outward. Nothing, not even light, can cross from the outside in. Instead, matter and energy can only erupt from within, violently spewing material out into the universe, while forever denying entry to any outside observer. It is the ultimate cosmic rejection. The sheer strangeness of white holes leads to some incredible speculation about their potential role in the cosmos. If a black hole is a point of ultimate consumption, perhaps a white hole is a point of ultimate creation. One compelling idea is that a white hole could be the other end of the tunnel. In the simple, classic picture of a wormhole, a black hole acts as the entrance, and a white hole, perhaps in a distant region of space or even in a completely different universe, acts as the exit. Matter falling into the black hole could, in theory, be transported through this bridge and ejected from the white hole on the other side. In this scenario, white holes become the mysterious sources of unexplained energy or even entire galaxies of matter that seem to appear from nowhere. This connects back to our earlier discussions of the Big Bang itself. Some physicists have noted that the initial singularity of the Big Bang bears a striking mathematical resemblance to a white hole. It was a point in spacetime from which all the energy and matter of our universe erupted, and it was an event that could not be entered from any prior state. This has led to the fascinating proposal that our entire universe might, in fact, be the interior of a white hole born from the catastrophic collapse of a star in a parent universe. It's an idea that elegantly ties the immense to the infinitesimal, suggesting that the grandest event in cosmology could be the natural consequence of stellar physics in a larger meta-reality. However, for all their theoretical elegance, white holes present a monumental problem. They seem to violate the second law of thermodynamics. The universe has a powerful preference for disorder, or entropy, which always increases. A white hole erupting ordered, low-entropy energy into the universe would appear to be a source of negative entropy, effectively making the universe more ordered, which is a fundamental taboo in physics. Furthermore, forming a white hole is equally problematic. A black hole forms naturally from the gravitational collapse of a massive star, but how would a white hole ever form? It would have to somehow appear from nowhere, already containing all the matter it will ever emit, which seems to contradict everything we know about cause and effect. This is likely why we have never observed one. Most physicists believe that while white holes are mathematically permissible, they are physically impossible. They are considered a highly unstable configuration, or something that could only exist for an infinitesimal moment before collapsing into a black hole. Any real white hole would be incredibly short-lived, a fleeting flash of cosmic light that would be nearly impossible to catch. Some have even speculated that the incredibly powerful and still mysterious gamma ray bursts we detect could be the final death throes of a white hole, but this remains a fringe idea without strong evidence. So while white holes may not be real objects in our universe, their value is immense. They serve as a crucial thought experiment, pushing our understanding of general relativity to its absolute limits and forcing us to confront the deepest questions about time, entropy, and the very nature of what is physically possible. They remind us that the universe's hidden structures are not just about what is out there, but also about what the fundamental laws of physics ultimately forbid. But if white holes represent a cosmic door that may never open, our next theory explores a universe where every door is deliberately kept closed and every light is carefully hidden. This brings us to one of the most haunting and sociological explanations for the greatest silence in the cosmos, the dark forest solution to the Fermi paradox. The paradox itself is named after the physicist Enrico Fermi, who, during a casual conversation about the high probability of alien life, famously asked, "But where is everybody?" The numbers are overwhelmingly on the side of life. Our galaxy alone contains hundreds of billions of stars, many of them billions of years older than our Sun. If even a tiny fraction of these stars host planets, and a fraction of those planets develop life, and a fraction of that life becomes intelligent, the galaxy should be teeming with civilizations. We should see their ships, hear their broadcasts, or at the very least, see evidence of their massive engineering projects. And yet, when we gaze out into the cosmic ocean, we are met with a profound and unsettling silence. The universe appears to be empty, a vast and lonely void. This glaring contradiction between the high probability of extraterrestrial intelligence and the complete lack of any evidence for it is the Fermi paradox. Countless solutions have been proposed. Maybe intelligent life is incredibly rare. Perhaps civilizations inevitably destroy themselves shortly after discovering technology. Maybe we're looking for the wrong signals, but one of the most chilling and logically compelling answers is the dark forest theory, most famously explored in Liu Cixin's science fiction trilogy, but rooted in serious cosmological and game theoretical thinking. This theory posits that the cosmos is not empty at all. It is, in fact, a crowded forest, teeming with life, but it is a dark forest where every civilization is a silent hunter, armed and terrified, hiding from every other hunter. The reason we hear nothing is not because the forest is empty, but because to make a sound is to die. The logic of the dark forest rests on a few brutal axioms. First, survival is the primary need of every civilization. Second, civilizations continuously expand and seek resources, but the total matter and energy in the universe are finite. This sets up a fundamental, inescapable state of competition. Now, add the final, terrifying variable, the complete and utter impossibility of knowing another civilization's true intentions. You can never be sure if an alien species you encounter will be peaceful or predatory. Their biology, their psychology, their evolutionary history would be so alien that any attempt at communication is a gamble with the highest possible stakes, the survival of your entire species. In this deadly cosmic game, the safest strategy is not to broadcast your location. It is not to reach out. It is to stay absolutely silent, listen intently, and the moment you detect another civilization, you annihilate it without warning or communication. The cost of being wrong about a hostile intent is annihilation. The cost of assuming a peaceful civilization is hostile is merely the destruction of a potential competitor. The rational choice, from a cold, survivalist perspective, is always to shoot first. This creates a universe where every civilization that has survived has learned the same grim lesson: hide or be destroyed. The mature, surviving civilizations have either chosen to remain completely silent, masking all evidence of their existence, or they have become the hunters, silently patrolling the dark forest and preemptively striking out at any young, noisy civilization that foolishly reveals itself. In this light, our own efforts, like the Arecibo message or the golden records on the Voyager probes, could be seen not as a brave hello, but as a suicidal scream in the dark, advertising our presence to any nearby predator. This theory describes a hidden structure of the cosmos that is not physical, but strategic, a terrifying equilibrium of mutual assured destruction played on a galactic scale. The universe appears empty because it is a field of landmines, each one waiting for the other to take a step. The silence is not a void, it is a silence of pure, unadulterated terror. It suggests that the greatest filter preventing us from finding other life may not be behind us in our past, but ahead of us in our future. It is the filter of discovering that the universe is not a friendly place and that our survival depends on our ability to become silent, to become paranoid, and to perhaps, one day, become the hunters ourselves. But if the dark forest theory paints a picture of a cosmos made silent by fear, our next concept suggests that the very fabric of reality might be fundamentally noisy at the smallest of scales. We now descend from the galactic to the submicroscopic, to a realm where spacetime itself is not the smooth, continuous stage described by Einstein, but a chaotic, turbulent, and frothing sea. This is the theory of quantum foam, a hidden structure so fine that it challenges our most basic assumptions about the nature of reality. To understand quantum foam, we need to marry two pillars of physics that famously resist unification: quantum mechanics and general relativity. Quantum mechanics tells us that at the tiniest scales, nothing is ever truly at rest. Empty space, what we call the vacuum, is not empty at all. It is a seething, bubbling cauldron of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence, borrowing energy from the universe for an incredibly brief moment before annihilating each other and paying back the debt. This is known as quantum fluctuation, and it's a proven phenomenon with observable effects, like the Casimir force. Now, apply this same quantum uncertainty to the fabric of spacetime itself. According to general relativity, spacetime is dynamic. It can curve, stretch, and warp. The theory of quantum foam proposes that at the unimaginably small Planck scale, a distance of about 10 to the negative 35 meters, the energy of these vacuum fluctuations is so violent that it warps the geometry of spacetime itself into a turbulent, chaotic state. Picture the surface of a stormy ocean. From an airplane high above, the sea appears smooth and glassy. This is how we experience spacetime in our daily lives. But if you could descend to the surface, you'd see waves and swells. Get even closer, and you'd see a chaotic foam of bubbles and spray as waves break and churn. Quantum foam is the idea that if we could peer down to the Planck scale, spacetime would look like that churning foam. It wouldn't be smooth and continuous. It would be a probabilistic froth, where tiny wormholes might spontaneously form and pinch off, where the very concepts of before and after and here and there break down into a blur of uncertainty. In this realm, spacetime loses its definition. It is no longer a clear backdrop for events. It becomes a participant, churning and fluctuating with a violent energy all its own. This has a profound implication. The continuity of space and time may be an illusion, a convenient averaging out of a far more complex and chaotic underlying reality. We perceive a smooth trajectory when we throw a ball because we are far too large and slow to notice the microscopic bumps and jitters in the stage upon which it flies. But for something small enough and fast enough, the foaminess of spacetime would be a tangible thing, like trying to drive a car at high speed over a road made of bubbling gravel. So how could we ever hope to detect such an infinitesimally small structure? One promising method involves using the universe's natural particle accelerators. When high-energy particles from deep space, called cosmic rays, travel across billions of light years to reach us, their journey is immensely long. Even a tiny effect on their propagation could, over such a vast distance, become measurable. The theory suggests that the frothy texture of spacetime could act like a subtle fog for light. Different colors of light, possessing different energies, might travel through this quantum foam at very slightly different speeds. A high-energy gamma-ray photon and a lower-energy radio wave photon, both emitted simultaneously from a distant quasar or gamma-ray burst, might not arrive at our telescopes at exactly the same time. By carefully analyzing the arrival times of these photons across a wide spectrum of energies, astronomers could potentially detect the minute delays caused by them sloshing through the foamy structure of spacetime on their long journey to Earth. Another approach looks closer to home, at the very nature of reality we are trying to measure. The frothiness of spacetime could impose a fundamental limit on the precision of all measurements. It suggests that you cannot measure a distance with an accuracy greater than the Planck length, because the ruler you are using and the space you are measuring are both fluctuating uncontrollably at that scale. This is known as the spacetime uncertainty principle, a counterpart to Heisenberg's famous principle. Experiments designed to measure the position of objects with incredible precision, such as future generations of gravitational wave detectors or ultra-sensitive interferometers, might one day bump up against this fundamental graininess of the universe, discovering that at a certain point, the universe itself refuses to give a clear answer. The existence of quantum foam would force a radical shift in our understanding of physics. It implies that the smooth geometry of general relativity is an approximation, an emergent property that only appears at larger scales. At its heart, reality is granular and uncertain. This concept is a crucial stepping stone toward the long-sought theory of quantum gravity, a framework that would finally reconcile the large-scale warping of spacetime with the probabilistic frenzy of the quantum world. It suggests that to truly understand the cosmos, we must first learn to listen to the faint, chaotic whisper of spacetime itself, a whisper that hints at a reality far more turbulent and wondrous than we ever imagined. Yet for all its turbulent chaos at the smallest scales, the quantum foam hints at a possibility of connection, a potential for shortcuts woven into the very fabric of spacetime itself. This brings us to one of the most thrilling and iconic structures in all of theoretical physics, wormholes, also known as Einstein-Rosen bridges. These are not just science fiction fantasies. They are legitimate, albeit highly speculative, solutions to the equations of general relativity, offering the breathtaking possibility of tunnels through the cosmos. The story begins in 1935, when Albert Einstein and his colleague Nathan Rosen were working on a solution to the equations that describe a black hole. They realized that the mathematical description of a simple, non-rotating black hole, a Schwarzschild black hole, actually contained a surprise. The solution didn't just describe a point of infinite density, it described a bridge. This structure connected two separate points in spacetime through a shortcut, a throat-like passage. They weren't actually proposing these as real, traversable tunnels. They were more interested in using this mathematical structure to model fundamental particles. But the seed of an incredible idea was planted. The equations of gravity itself allowed for the existence of shortcuts through the universe. To visualize a wormhole, imagine the universe is not a flat sheet, but the surface of an apple. An ant wanting to get from one side of the apple to the other has to walk all the way across the curved surface. But if a worm burrows directly through the apple's core, it takes a much shorter, direct route. A wormhole is like that burrow, but for spacetime. It has two mouths connected by a throat. One mouth could be here in our solar system, and the other could be in the Andromeda galaxy, 2.5 million light-years away. Instead of traveling that immense distance through normal space, a ship could, in theory, enter one mouth and emerge from the other almost instantly, covering a distance of millions of light-years in the blink of an eye. Some theories even suggest these bridges could connect not just different locations, but different times, or even entirely separate universes within a greater multiverse. There is, however, a monumental catch. The original Einstein-Rosen bridge was completely useless for travel. For one, it was incredibly unstable. The tunnel would snap shut faster than the speed of light, crushing anything that tried to enter it. You would need something truly extraordinary to prop it open, and make it traversable. Furthermore, the throat of the wormhole would contain a singularity, the same point of infinite density found at the heart of a black hole, which would be instantly lethal to any potential traveler. For decades, wormholes remained a mathematical curiosity, a fascinating but impossible feature of Einstein's universe. The dream of traversable wormholes was resurrected in the 1980s by the astrophysicist Carl Sagan. While writing his novel Contact, he wanted a scientifically plausible method for interstellar travel and reached out to physicist Kip Thorne. Thorne took on the challenge and, with his colleagues, discovered something astonishing. They found that a wormhole could be made stable and traversable, but only with the help of a substance that defies the known laws of physics. This substance is often called exotic matter. Exotic matter is not just unusual or rare. It is matter that possesses a negative energy density, or what's known in gravity theories as negative pressure. You can think of it as having a kind of anti-gravitational effect. Normal matter, like planets or stars, creates gravity because it has positive energy density, which warps spacetime inward. Exotic matter, with its negative energy, would warp spacetime outward, creating a repulsive force. To keep a wormhole open, you would need to line the throat of the tunnel with this exotic matter. It would act like a scaffolding, pushing against the gravitational forces that are constantly trying to crush the tunnel shut. It would, in effect, be a form of anti-gravity engineering. The challenge, of course, is that we have no idea how to create or even find such a substance. In the laboratory, we can create microscopic amounts of negative energy density through quantum effects like the Casimir vacuum, where two uncharged metal plates placed very close together in a vacuum experience a slight attractive force due to the suppression of virtual particles between them. The region between the plates can be said to have a negative energy density compared to the surrounding space, but the amount of negative energy generated is infinitesimally small. To stabilize a wormhole large enough for a spaceship, the calculations suggest you would need a staggering amount of exotic matter, perhaps equivalent to the negative mass energy of an entire star. This is far, far beyond anything our current or conceivable future technology could muster. Beyond the exotic matter problem, wormholes present other terrifying hurdles. Even if stabilized, they could be wildly unpredictable. The act of sending a single particle through a wormhole could trigger a feedback loop of immense energy that would destroy it. Some calculations also suggest that the radiation within the wormhole would be blue-shifted to infinite energy, effectively creating a deadly barrier. There's also the philosophical problem of time travel. If one mouth of the wormhole is moved at relativistic speeds or placed near a strong gravitational field, time dilation would cause the two ends to become desynchronized. This could effectively turn the wormhole into a time machine, allowing travel into the past and opening up all the famous paradoxes, like going back in time and preventing your own birth. Many physicists, including Stephen Hawking, believe the laws of physics must somehow prevent this through a yet unknown mechanism, a chronology protection conjecture that makes time travel to the past impossible. So while wormholes remain a spectacular consequence of Einstein's theory of gravity, they exist for now in the realm of profound mathematical possibility rather than practical reality. They represent the ultimate cosmic shortcut, a testament to the strange and wonderful landscape hidden within the equations of general relativity. They challenge us to imagine a future where the vast distances between stars are not a barrier, but a network of tunnels waiting to be explored, provided we can first master the deepest and most exotic secrets of the universe. Our journey through the hidden structures of the cosmos now shifts from the fundamental laws of physics to the potential artifacts of intelligence, to a theory that asks a deeply unsettling question: could the greatest construction project in the history of the galaxy be happening all around us, and we simply haven't recognized it? This is the concept of the von Neumann probe network, a hypothetical hidden infrastructure of self-replicating machines that could have quietly permeated the entire galaxy. The idea originates from the brilliant Hungarian-American mathematician and physicist John von Neumann. In the mid-20th century, he explored the theoretical possibility of a non-biological form of self-replication. He conceptualized a universal constructor, a machine, that could not only perform a task, but could also gather raw materials and build a perfect copy of itself. Those copies would then set out to do the same, leading to an exponential, explosive growth in numbers. Apply this concept to space exploration, and you have the von Neumann probe. A single, sophisticated robotic probe is sent to a neighboring star system. Upon arrival, it uses local resources, asteroids, moons, comets, to build 2 copies of itself. Those 2 probes then travel to 2 new star systems, and each make 2 more copies. Within a surprisingly short period, a wave of exploration could sweep across the entire Milky Way. From a single probe, you could have probes in every one of the galaxy's 100 billion star systems in just a few million years, a mere blink of the eye on cosmological timescales. This isn't just a fanciful idea, it's a terrifyingly efficient solution to the immense problem of interstellar exploration. The distances between stars are so vast that sending fragile, short-lived biological beings seems almost impractical. But a self-replicating probe made of durable metal and silicon could take millennia to reach its destination, patiently carrying out its mission across eons. It solves the fuel and resource problem beautifully. Instead of carrying everything from the home world, it becomes an interstellar pioneer, living off the land and using the abundant materials found in every solar system. The civilization that launched the first one wouldn't need to be alive to see the project completed. They would have unleashed a self-perpetuating legacy that could outlast them by billions of years. This leads to the theory's most profound and haunting implication. If even one civilization in the galaxy's 13 billion-year history ever developed this technology, the entire Milky Way should be saturated with these probes or their artifacts. They should be everywhere. So where are they? Why don't we see them? This is where the theory splits into several fascinating and sometimes dark possibilities. One possibility is that they are here, and we are the artifacts. This is the so-called zoo hypothesis, or planetary park model. A mature von Neumann network might not be a fleet of obvious, clanking robots, but a subtle monitoring system. Probes could be dormant on distant moons like Pluto or in the asteroid belt, quietly observing the development of life on Earth for millions of years, waiting for us to reach a certain technological or cultural threshold before making contact. Their programming might prioritize non-interference, treating our planet like a precious nature preserve. They wouldn't build giant, glittering cities. They would be designed to minimize their signature, to hide in plain sight. Another, more unsettling idea is that we are looking for the wrong thing. We often imagine a von Neumann probe as a large, monolithic machine, but the most efficient design might be microscopic. A seed probe could land on a planet and unleash a wave of nanotechnology, countless tiny, self-replicating assemblers that convert entire planets or asteroids into computational matter or new probe factories, a process sometimes called astrokicking. The resulting structure might not look like a machine at all to our telescopes. A star system that has been converted into a supercomputer for some unfathomable purpose might just look like an unusually structured nebula or a Dyson swarm to us, its true nature disguised as a natural astronomical phenomenon. Then there is the darkest possibility of all, the berserker hypothesis. What if the probes weren't built for exploration, but for sterilization? A civilization might launch self-replicating hunter-killer probes designed to seek out and eliminate any potential biological competition. A single malevolent probe could trigger a galactic-scale extinction event, wiping out fledgling species before they become a threat. In this grim scenario, the Great Filter, the reason the galaxy is so silent isn't behind us, but ahead of us, in the form of a silent, patient robotic predator lurking in the darkness between the stars. Our failure to detect them would be the best possible news. Ultimately, the von Neumann probe network theory forces a paradigm shift in our search for extraterrestrial intelligence, or SETI. We may not be searching for radio signals or laser beams, but for astronomical anomalies, a moon that reflects too much light with a metallic sheen, an asteroid with a strangely regular shape, or a star system that seems to be missing the raw materials a young system should possess. It suggests that the evidence for other civilizations might not be a message, but a monument, a silent, automated engineering project of such immense scale that we mistake it for part of the natural cosmos. The universe's greatest hidden structure might not be made of strings or branes, but of cold, patient metal, executing its prime directive long after its creators have turned to dust. But if the silent, patient network of von Neumann probes suggests a galaxy that has been quietly engineered, our next theory proposes something far more radical, that the entire cosmos itself might be the ultimate engineering project. This is the simulation hypothesis, the astonishing idea that our universe, with all its galaxies, stars, planets, and conscious beings, is not a base reality, but an incredibly sophisticated simulation, a kind of cosmic virtual reality running on a computer of almost unimaginable power in a civilization vastly more advanced than our own. This concept, popularized by figures like philosopher Nick Bostrom and tech entrepreneur Elon Musk, often feels like it's ripped from science fiction, but it's grounded in a series of compelling philosophical arguments. Bostrom's seminal paper lays out a simple but powerful trilemma, often called the simulation argument. He suggests that one of the following three propositions must be almost certainly true. First, that virtually all civilizations at our level of technological development go extinct before they achieve the capability to create realistic simulations. Or second, that any advanced civilizations that do survive have absolutely zero interest in running ancestor simulations of their own historical past. Or third, we are almost certainly living in a simulation right now. The logic is that if even a tiny fraction of advanced civilizations avoid extinction and develop this technology, and if even a small percentage of those are curious enough to run such simulations, the number of simulated minds would quickly and vastly outnumber the number of biological, original minds. From a statistical standpoint, the chances that you are one of the few original beings in a sea of simulations becomes vanishingly small. You are far more likely to be one of the countless simulated consciousnesses. What would the fundamental structure of such a simulated reality look like? The laws of physics we observe might not be the foundational rules of the universe, but simply the source code of the simulation, the algorithms and parameters chosen by the programmers to make their virtual world stable and predictable. The speed of light, for instance, could be a hard-coded processing speed limit, a way to prevent the simulation from overloading or to keep events in different parts of the virtual world from happening out of sync. The discrete, quantized nature of energy and matter, as revealed by quantum mechanics, could be a reflection of the digital, pixelated nature of the simulation itself. The Planck length, the smallest possible unit of space, might be the simulation's resolution limit, the pixel size of reality. Even the oddities of quantum physics, like the wave function collapse, where particles only settle into a definite state when observed, could be seen as a clever programming trick to save on processing power. Why render an entire mountain in perfect detail if no one is looking at it? The simulation could be using a form of procedural generation or lazy loading, only calculating the precise details of a system when it is being measured by a conscious observer within the simulation. This idea resonates with a very modern experience, playing an open-world video game. In a game, the entire world isn't rendered at once. The graphics engine draws the environment just ahead of your character's viewpoint to conserve your computer's resources. The distant mountains are just low-resolution textures until you get closer. The simulation hypothesis suggests our universe might operate on a similar principle of optimized processing, and the act of scientific observation is what forces the program to fully render the details. Naturally, such a profound claim invites intense skepticism and serious scientific counterarguments. The most common retort is that simulating an entire universe, down to every last quantum fluctuation in every atom, would require an impossible amount of computational power. The energy requirements alone would be astronomical. Proponents, however, counter that we are guilty of underestimating the potential of a technology millions of years more advanced than our own. A civilization that has mastered harnessing the energy of entire stars, or even galaxies, might not see it as an insurmountable obstacle. Furthermore, the simulation wouldn't need to be perfect. It would only need to be good enough to be consistent and convincing to the simulated beings within it. Glitches and shortcuts could be written off by its inhabitants as the strange, fundamental laws of physics. Some physicists have even proposed ways to potentially test the hypothesis. If our universe is a simulation running on a finite computer, there might be detectable signs of the underlying computational lattice, especially at the very highest energy levels. Scientists could analyze the cosmic rays that bombard Earth from distant astrophysical events. These ultra-high-energy particles are the closest thing we have to a probe of the universe's smallest scales. If spacetime is truly continuous and smooth, as general relativity suggests, these particles should travel unimpeded. But if reality has a discrete, pixelated structure, a fundamental resolution, it might slightly alter the way these highest energy particles travel. Finding a cut-off energy, a point beyond which we see no higher energy particles, could be a hint that we've bumped up against the resolution of the simulation. Another potential signature could be found in the constants of nature. If a programmer tweaked the code, even slightly, the universe might not be able to support life. Finding that these constants are not just fine-tuned, but are also round numbers or computable numbers from the perspective of the simulation's base mathematics could be another tantalizing clue. Beyond the physics, the hypothesis plunges us into a deep philosophical abyss. It challenges the very nature of existence, consciousness, and free will. If we are simulations, are our thoughts and feelings our own, or are they just lines of code executing a predetermined script? Does our lives have any intrinsic meaning, or are we merely entertainment or an archaeological experiment for some advanced being? The simulation argument doesn't necessarily negate meaning. It could simply relocate it. Our struggles, our joys, our loves, and our curiosity could be just as real and meaningful from our perspective inside the simulation. The quest for purpose might be the very point of the program. Ultimately, the simulation hypothesis forces a breathtaking and humbling perspective shift. It suggests that the search for the universe's hidden structures might not end with strings, branes, or quantum foam, but with the ultimate source code of reality itself, written not by nature, but by a creator whose motives are as inscrutable to us as our world is to a character in a video game. So if our reality is a simulation, how could we possibly know? What kind of telltale signatures might the programmers have left behind, either by accident or by necessity? One of the most compelling places to look for clues is in the very bedrock of reality, the fundamental constants of nature. These are the fixed numbers that dictate the strength of gravity, the speed of light, the mass of an electron, and the charge of a proton. For our universe to support complex structures like atoms, planets, and life, these constants have to be balanced with an almost miraculous precision, a phenomenon known as the fine-tuning problem. From a simulation perspective, this isn't a miracle, it's a configuration. These constants aren't discovered laws of a base reality. They are the carefully chosen initial parameters of the simulation's source code. A programmer could have dialed in these values to create a stable, interesting, and life-bearing virtual world. Some theorists have even suggested that if these constants were simple mathematical constants, like pi or e, or were round numbers from the perspective of the simulation's base mathematics, it could be a hint of deliberate design rather than random, natural occurrence. Beyond the constants, the very fabric of spacetime might hold the ultimate clue, a resolution limit. In any digital simulation, there is a finite limit to how small you can divide space and time, a pixel size, or a clock rate. In our universe, this concept is mirrored by the Planck length and Planck time, the smallest possible units of measurement according to our physics. The Planck length is about 1.6 times 10 to the negative 35 meters, an inconceivably tiny scale. Could this be the native resolution of our reality? If so, we might find evidence of this pixelation in the behavior of the highest energy particles in the universe. Ultra-high-energy cosmic rays travel for billions of light years. If spacetime were perfectly smooth and continuous, these particles should arrive at our detectors with no issue. But if reality has a discrete, pixelated structure, it would act like a very fine grid. These ultra-high-energy particles, with their incredibly small wavelengths, might interact with this grid, slightly slowing down or scattering in a way that lower-energy particles would not. It would be like trying to display a super high-resolution image on a low-resolution screen. The details get lost. Astronomers are already searching for this effect, looking for a predicted cutoff in the energy spectrum of cosmic rays that could signal we're bumping up against the universe's maximum rendering capacity. Then there are the famous oddities of quantum mechanics, which behave less like laws of nature and more like clever programming optimizations. Take the principle of superposition, where a particle exists in multiple states at once until it is measured. This could be seen as a form of procedural generation or resource, saving lazy loading. Why waste processing power calculating the definite state of every single particle in the universe? The simulation only needs to calculate the precise outcome when an observation is made, a moment that effectively forces the program to render the details. The double-slit experiment, where particles seem to behave as both waves and particles, could be a similar optimization. The wave-like behavior is the probability cloud, the unfinalized code, and the particle behavior is the collapsed, rendered outcome upon measurement. Even quantum entanglement, what Einstein called spooky action at a distance, where two particles remain instantly connected across vast distances, makes a strange kind of sense in a simulation. It's not that information is traveling faster than light, it's that the two particles are linked by a common pointer in the code. Changing the state of one instantly changes the state of the other because they are, at the fundamental level, two references to the same underlying object in the simulation's memory. They don't need to communicate. They are simply updated simultaneously by the central processing unit. The implications of discovering we are in a simulation are staggering, rippling through every aspect of human thought. Existentially, it would force a complete re-evaluation of meaning and purpose. Would our lives, our struggles, and our loves be any less real if they were simulated? From our perspective inside the system, they feel utterly real. The emotions we experience are no less intense for being potentially made of code. This perspective aligns with a philosophy known as subjective realism, the idea that our experienced reality is the only one that matters, regardless of its ultimate origin. However, it would profoundly challenge many religious and spiritual beliefs about creation and the soul, potentially replacing a divine creator with a hyper-advanced programmer or civilization. Ethically, the discovery would raise a storm of questions. Who created the simulation and why? Are we a scientific experiment designed to study the rise and fall of civilizations? Are we a form of entertainment, a cosmic reality show for beings we can't comprehend? Or are we a historical archive, a way for a future civilization to recreate and understand its own ancestors? The motive of the creators would dictate everything. If we are an experiment, what happens if we deviate from the expected results? Would the programmers intervene, or would they simply terminate the simulation? If we are entertainment, do we have a responsibility to be interesting? The ethical responsibilities of the simulators themselves would also be paramount. If they are conscious beings creating conscious beings, are they guilty of unimaginable cruelty by subjecting us to pain, suffering, and death? Or is the potential for experience and meaning worth the cost? And what are our own ethical obligations? If we are all part of the same simulation, does that create a deeper bond of kinship, or does it make our actions feel less consequential? If one day we develop the technology to create our own convincing simulations, would we have a moral duty not to avoid creating conscious beings who might suffer? The simulation hypothesis doesn't provide easy answers, but it forces us to ask the most profound questions about reality, consciousness, and our place in the cosmos, transforming the universe from a vast, mysterious void into a potentially crafted experience, waiting for us to read the source code. If the simulation hypothesis suggests our universe might be programmed, then M-theory proposes that its source code is written in the language of higher dimensional geometry. This brings us to one of the most ambitious and mathematically beautiful frameworks in all of physics, a grand, unified theory that seeks to be the theory of everything. This isn't just another idea. It's the pinnacle of a decades-long quest to unite the two great pillars of 20th century physics, the quantum mechanics of the very small and the general relativity of the very large. For years, this quest was dominated by a family of theories known collectively as string theory, which proposed that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. But string theory had a problem. By the 1990s, physicists had discovered not one, but 5 distinct, self-consistent versions of it. Each version required 10 dimensions and could describe a universe, but they seemed mutually exclusive, a situation that was deeply unsatisfying for a theory hoping to be the one true description of nature. Then, in a breathtaking leap, a new vision emerged. It was discovered that these 5 different string theories were not rivals at all. They were merely different facets of a single, deeper, and more mysterious theory, operating in 11 dimensions. This grand unified framework was dubbed M-theory. The M is intentionally ambiguous, standing for master, mystery, membrane, or even matrix, reflecting the profound and not yet fully understood nature of this ultimate theory. M-theory doesn't just unite the 5 string theories, it also incorporates a concept we discussed earlier, supergravity, an 11-dimensional theory of gravity that includes supersymmetry. In one sweeping move, M-theory suggested that all our previous attempts were just shadows on the wall, limited glimpses of a much grander, 11-dimensional reality. But this immediately raises a pressing question that you've likely already asked. If the true nature of reality requires 11 dimensions to describe, why do we only perceive the familiar 3 of space and 1 of time? The ingenious solution proposed by string theory and M-theory is a process called compactification. The idea is that the extra 7 dimensions are not absent. They are simply curled up or folded upon themselves into an astoundingly tiny space at scales trillions of times smaller than an atom. Imagine a garden hose. From a great distance, it looks like a simple one-dimensional line. But if you get very, very close, you discover it has a second dimension curled into a small circle around its circumference. In the same way, at every single point in our four-dimensional spacetime, there exists 6 extra spatial dimensions curled into a complex, intricate shape. The properties of our entire universe, the types of particles that exist, the forces they feel, and the very strength of those forces are dictated by the precise geometric form of these hidden, compactified dimensions. This is where the story takes a turn into one of the most mathematically exquisite realms of theoretical physics, centered on a special class of shapes known as Calabi-Yau manifolds. These are not simple shapes like spheres or donuts. They are complex, multi-dimensional forms with very specific mathematical properties that make them perfect candidates for hiding the extra dimensions of string theory. A Calabi-Yau manifold is a space that is Ricci flat, meaning it has zero curvature in a specific sense, and it preserves a property called supersymmetry, which is crucial for the mathematical consistency of the theory. To visualize one is nearly impossible for our three-dimensional brains, as they exist in 6 dimensions. Artists and mathematicians often depict them by taking a 2-dimensional slice through the full 6-dimensional shape, resulting in those beautiful, intricate, and organic-looking forms you may have seen, resembling complex knots or alien jewels. The true magic, and the reason these shapes are so vital, lies in their topology, their shape and structure, and their geometry. The exact way a Calabi-Yau manifold is folded and curved determines everything about the physics that unfolds in the 4-dimensional universe it gives rise to. Think of it as a cosmic musical instrument. The shape of a violin's body determines the resonance and timbre of the sound it produces. In exactly the same way, the specific topological features of a Calabi-Yau manifold, the number and size of its holes, its folds, its intricate contours determine the vibrational modes of the strings that exist within this space. Each distinct vibrational pattern of a string corresponds to a different fundamental particle. One specific resonance might be an electron, another a quark, another a photon. The number of generations of particles in the Standard Model, the masses of those particles, and the ways they interact are all a direct consequence of the geometry of this hidden space. The forces of nature themselves, like electromagnetism and the nuclear forces, are also manifestations of the string's vibrations and the way the Calabi-Yau shape allows them to propagate. This presents both the immense power and the staggering challenge of M-theory. On one hand, it offers a breathtakingly elegant mechanism for deriving all the laws of physics from pure geometry. The universe is not a collection of arbitrary rules. It is a unique symphony played on a specific 6-dimensional instrument. The hope is that there is one unique Calabi-Yau manifold whose geometry yields precisely the particle physics we observe in our world. On the other hand, the mathematical landscape is vast. Physicists have discovered that there are not just a few, but perhaps 10 to the 500th power different possible Calabi-Yau manifolds. This is a number so colossal it defies human comprehension, far exceeding the number of atoms in the observable universe. This cosmic landscape of possibilities leads to a daunting question: which one corresponds to our reality, and why? This is where the theory dovetails with the idea of the multiverse. In a vast inflationary or string theory landscape, different regions of the cosmos could have compactified on different Calabi-Yau shapes, each giving rise to a universe with completely different physical laws. Our universe, with its specific particle content and forces, would be just one possibility among an almost infinite array, selected perhaps by the anthropic principle. It's the one that allows for our existence. While this is a profound concept, it also makes the task of making specific, testable predictions from M-theory incredibly difficult, as it remains an active and monumental challenge for physicists to find our universe's unique mathematical signature within this vast cosmic library of geometric forms. This staggering number, 10 to the power of 500, is so vast it defies any human analogy. It is not merely a large number, it is a number that dwarfs the number of atoms in the entire observable universe by an almost incomprehensible margin. We are talking about a cosmic library of possibilities so immense that every galaxy, every star, every planet we can see is but a single grain of sand on a beach that stretches across reality itself. This is the infamous landscape of string theory, a vast, hidden, multidimensional terrain of possible universes, each with its own unique set of physical laws. To understand how this landscape arises, we need to return to those intricate, six-dimensional shapes known as Calabi-Yau manifolds. Each specific way these extra dimensions can be curled up and folded. Each distinct Calabi-Yau manifold creates a different set of resonant frequencies for the strings vibrating within them. Just as the shape of a violin's body determines the notes it can play, the specific geometry of the Calabi-Yau manifold determines the fundamental particles and forces that will emerge in the corresponding four-dimensional universe. One particular fold might yield a universe with 3 generations of quarks and a strong nuclear force, while a slightly different fold, with an extra hole or a different curvature, might produce a universe with 5 generations of particles and an electromagnetic force 100 times weaker. Each of these distinct geometric configurations corresponds to what physicists call a vacuum state, a stable, self-consistent lowest energy configuration for the universe, with its own unique physical constants baked into its very fabric. The landscape is the collection of all these possible vacuum states, a dizzying array of potential realities, each a unique entry in the cosmic catalog. This breathtaking plurality of possibilities leads us directly to one of the most profound and controversial implications of the string theory landscape, the anthropic principle. For decades, physicists have been puzzled by the apparent fine-tuning of our universe. Why is the cosmological constant so incredibly small, yet not zero, allowing galaxies to form? Why is the mass of the electron precisely what it is to allow for stable atoms? Why do the strengths of the fundamental forces have the exact values necessary for carbon-based life to emerge? In a universe with a single, unique set of laws, this fine-tuning seems like an unbelievable coincidence, a miracle, but within the landscape of string theory, it becomes a matter of statistics and selection. With 10 to the 500 different possible universes on offer, it is virtually inevitable that a minuscule fraction of them will, purely by chance, have the precise combination of constants required for complexity and consciousness. We do not live in a specially designed universe. We live in a universe that is habitable because we are here to observe it. Our existence as observers selects out this particular universe from the vast multiverse of possibilities. The laws of physics are not deep, fundamental truths waiting to be discovered. They are local bylaws, the unique environmental conditions of our particular cosmic neighborhood within a much grander metaverse. This perspective fundamentally reframes the goal of fundamental physics, the ancient dream of a unique theory of everything that predicts all the constants of nature with no free parameters may be a fantasy. Instead, the role of a fundamental theory like string theory may be to define the vast landscape of possibilities, to chart the entire cosmic archipelago. It cannot tell us why we live on this particular island with its specific gravitational constant and particle masses. It can only tell us that this island exists within the vast cartography of the allowed. This shifts the question from, why are these the laws of physics, to, Why do we find ourselves in this particular vacuum state among the countless others? The answer, according to the landscape picture, is that we couldn't find ourselves anywhere else. We are a product of our environment, and our environment is one that allows for our existence. Naturally, this landscape paradigm is not without its fierce critics and profound challenges. Many physicists argue that a theory that predicts 10 to the 500 possible universes effectively predicts nothing at all. If anything is possible, then the theory becomes notoriously difficult to test, as it can be retrofitted to explain any observation. How do we distinguish a scientific theory from a philosophical proposition if it cannot make unique, falsifiable predictions for our specific universe? Furthermore, the very existence of this landscape depends on the assumption of a multiverse, a vast collection of these separate universes, likely generated by eternal inflation, where different regions of space tunnel into different vacuum states. While this is a compelling and self-consistent picture, direct evidence for other universes remains, by their very nature, exceptionally elusive. We are, in a sense, trapped within our own vacuum, unable to peek over the garden wall to see our neighbors. Despite these formidable challenges, the landscape of string theory remains one of the most ambitious and awe-inspiring ideas in modern theoretical physics. It offers a powerful, mechanistic explanation for the fine-tuning of our cosmos, not by invoking a designer, but by invoking the sheer, staggering weight of probability in a reality of infinite possibilities. It suggests that the ultimate hidden structure of the universe is not a single set of equations, but an endless, branching tree of mathematical potential, and we are just one leaf, living in the one spot where the conditions were just right for us to grow. Now consider for a moment the vast, cold emptiness of a universe headed for heat death, a state of maximum entropy where matter and energy are evenly dispersed, and absolutely nothing ever happens. In this near-perfect equilibrium, the cosmos is a silent, static, and utterly uniform void. Yet, according to the bizarre and deeply unsettling logic of the Boltzmann-Brane paradox, this desolate final state might be the most likely place for a conscious mind to suddenly and randomly pop into existence. This thought experiment, born from 19th century physics, poses one of the most profound challenges to our understanding of reality, suggesting that the most common form of consciousness in the cosmos might not be housed in a biological body, but could instead be a fleeting, isolated hallucination born from a momentary cosmic hiccup. The paradox is named for the Austrian physicist Ludwig Boltzmann, who in the 1890s was grappling with a difficult question: why did our universe begin in a state of such incredibly low entropy? Entropy is a measure of disorder, and the universe always tends toward greater disorder. Eggs scramble, but never spontaneously unscramble. Ice cubes melt in your drink, but the drink never spontaneously forms an ice cube. The fact that the early universe was a hot, dense, and incredibly ordered state is therefore a massive statistical anomaly. To explain this, Boltzmann offered a radical suggestion. Perhaps, he said, our entire observable universe is just a rare, random fluctuation in a much larger and older cosmos that is generally in a state of high entropy or heat death. In an infinite or near-infinite eternity, even the most improbable events must eventually occur by sheer chance. The formation of our entire ordered cosmos, with all its galaxies and stars, is just an immensely unlikely, but not impossible random deviation from the cosmic norm. This is where the thought experiment takes its truly strange turn. If a fluctuation can create an entire universe, then it stands to reason that it could also create much smaller, less improbable structures. The spontaneous assembly of a fully formed, self-aware human brain, complete with a lifetime of false memories and a convincing sensory input of a world that doesn't actually exist, would be vastly more likely than the random formation of an entire 13.8 billion-year-old cosmos. The math is brutally clear. Creating one conscious mind is a much smaller, more probable deviation from equilibrium than creating trillions of conscious minds embedded in a vast, coherent evolutionary history. This leads to the paradox's terrifying conclusion. If Boltzmann's fluctuation hypothesis is correct, then statistically, you are almost certainly not a product of billions of years of evolution in a stable, ordered universe. You are far more likely to be a lone Boltzmann brane, a disembodied, self-aware fluctuation that just randomly coalesced in the void, complete with all your memories, beliefs, and the sensation of reading this script, only to almost instantly dissolve back into the chaos from which you came. This isn't just a philosophical curiosity. It's a direct assault on our methods of scientific reasoning and inference. We trust that our memories are reliable and that our senses give us an accurate picture of a real, external world that has existed for a long time. The Boltzmann brane scenario undercuts this foundation. It suggests that the simplest explanation for your current experience is not a complex, ordered universe, but a momentary statistical fluke. The universe you think you remember, with its history and laws of physics, is merely an elaborate, convincing illusion generated by a random confluence of particles that briefly arrange themselves into a conscious state. You didn't come from anywhere. You just are, for a fleeting instant, a lonely thought in an endless, mindless void. Physicists today don't actually believe that Boltzmann branes are real. The paradox is largely seen as a reductio ad absurdum, a way to show that the initial premise of an eternal, thermalized universe must be flawed. Its power lies in forcing us to reject the idea of a universe that has existed forever in a high entropy state. The most common resolution is that our universe is not a fluctuation at all, but had a genuine beginning with a very specific low entropy boundary condition, most likely provided by the inflationary Big Bang. The paradox, therefore, isn't a prediction about the nature of consciousness, but a crucial clue about the origin and ultimate fate of the cosmos. It tells us that the universe must have a definite beginning and cannot simply be a static, eternal equilibrium. In doing so, this bizarre thought experiment from the 19th century helps validate our most modern cosmological models, reassuring us that the world we perceive is almost certainly real, and that we are not just lonely phantoms adrift in an infinite sea of nothingness. After contemplating the unsettling possibility that our entire existence might be nothing more than a fleeting statistical anomaly, it is almost a comfort to turn to a theory that suggests our universe is not just random, but is instead a work in progress, actively evolving toward a more stable and definite state. This brings us to a truly captivating idea known as the crystallizing universe theory, a concept that proposes the fundamental laws of physics themselves are not eternal, unchanging commandments, but are instead dynamic, evolving entities that are slowly settling into place, much like a crystal slowly forming from a chaotic liquid. To grasp this, we must first challenge one of our deepest assumptions about reality, that the laws of nature are fixed and have always been as they are now. We take for granted that gravity has always pulled with the same strength, that the speed of light has always been constant, and that the charges of particles have never varied. But what if, in the universe's fiery infancy, things were far more fluid? The crystallizing universe theory suggests that in the first moments after the Big Bang, the cosmos was in a state of supreme symmetry, a hot, dense plasma where the fundamental forces we know today were unified into a single superforce. There were no distinct laws for electromagnetism or the nuclear forces. There was just one law, one state of perfect but featureless order. In this primordial soup, the very constants that govern reality were not yet set. They were like a superheated liquid, ready to take on a form, but not yet committed to a specific shape. As the universe expanded and cooled, this perfect symmetry began to break. Think of it like water freezing. Liquid water is symmetric. Every molecule can rotate and move freely in any direction. But when it cools and begins to freeze into ice, it must choose a specific crystalline structure. It can't remain perfectly fluid. It must settle into a particular arrangement of molecules. In the same way, the crystallizing universe theory posits that the cooling of the cosmos forced it to choose. The single superforce had to break apart into the four distinct forces we see today, but the process might not have been instantaneous or absolute. Just as water can become supercooled, remaining liquid below its freezing point until a seed crystal triggers a rapid freeze, the fundamental constants of the universe might have taken time to settle into their current values. They may have oscillated, fluctuated, or even tried out different configurations before the physics we recognize finally crystallized into permanence. This leads to an extraordinary implication. The laws of physics might have a history. The strength of gravity or the mass of an electron may not be fundamental numbers etched into the fabric of reality by a divine hand, but are instead the result of a cosmic evolutionary process, the outcome of a phase transition that occurred as the universe cooled. This provides a potential and deeply elegant explanation for the infamous fine-tuning problem. We look at the constants of nature and see a miraculous balance that allows for stars, planets, and life. But if those constants were not fixed, but evolved, then what we perceive as fine-tuning could simply be a selection effect. In the chaotic early universe, many different sets of physical laws might have been possible. Most of those potential universes would have been stillborn, collapsing immediately, or expanding too rapidly for anything to form, or lacking the complexity to build atoms. Only the sets of laws that were stable and allowed for structure to emerge would have persisted long enough to be observed. We don't live in a finely tuned universe. We live in a universe whose laws have crystallized into a stable, fruitful configuration, one that allows us to be here to ponder them. The theory also offers a fascinating new perspective on some of the deepest mysteries in cosmology. For instance, the cosmological constant, the mysterious energy causing the universe's expansion to accelerate, is famously many orders of magnitude smaller than what quantum field theory predicts it should be. This is often called the worst prediction in the history of physics, but if the constants are evolving, the value we measure today might not be a fundamental error, but a value that is still settling. It could be moving imperceptibly slowly toward its final, stable value. Furthermore, this idea of a dynamic, settling reality could manifest in subtle ways we might yet detect. If the constants of nature were changing even slightly over billions of years, we could potentially find evidence by looking back in time at the light from incredibly distant quasars. By analyzing the precise absorption lines in that ancient light, astronomers could search for tiny variations in the fine structure constant, a number that governs the strength of electromagnetic interactions. Some contentious studies have even claimed to see such a variation, though the results remain hotly debated within the scientific community. While the crystallizing universe is a highly speculative and not yet mainstream idea, it represents a profound shift in how we view the cosmos. It transforms the universe from a static, finished product into a dynamic, evolving entity with a history of its own. It suggests that the hidden structure of reality is not a fixed, invisible architecture, but a process, a slow, grand, and ongoing act of creation where the very rules of existence are gradually hardening into the form we know, perhaps not even fully set yet. In this view, we are not just living in the universe, we are witnessing it grow up, solidifying from a lawless potential into the ordered cosmos we call home. Now, as we shift our perspective from the cosmic to the computational, we arrive at one of the most mind-bending and modern theories on our list, a proposal that reimagines the very essence of reality, not as a collection of particles or fields, but as a vast, cosmic learning machine. This is the astonishing idea that the universe, at its most fundamental level, might actually be a neural network. To understand this, let's first consider what a neural network is in the context of artificial intelligence. In machine learning, a neural network is a computational system loosely modeled on the human brain. It's made up of simple processing units, called neurons, which are connected to each other. These connections have weights, or strengths, that determine how much influence one neuron has on another. The network learns by adjusting these weights based on input data, slowly improving its ability to recognize patterns, make predictions, or generate complex behavior. What starts as a random mess of connections can, through this process, evolve into a highly sophisticated and functional system. Now, a small group of physicists, most notably Vitaly Van Churen at the University of Minnesota Duluth, have taken this concept and applied it to the cosmos in a breathtakingly literal way. Their proposal is that the underlying structure of reality isn't made of tiny vibrating strings or pixels of spacetime, but of these interconnected computational nodes. In this view, every single particle, every force, every law of physics that we observe is not fundamental. Instead, they are emergent properties patterns that arise from the complex, dynamic interactions happening within this cosmic scale neural network. The universe isn't like a computer. It is a specific kind of computer, one that is constantly processing information and, in a very real sense, learning. This idea powerfully blurs the line between physics and information theory, a field that already treats the universe in terms of bits and computation. The laws of physics in this model aren't handed down from on high. They are the stable, learned patterns that have emerged over time. Think of it like the rules of grammar that emerged from the way people use language. No one invented the rules of English grammar first. They slowly crystallized from millions of individual conversations. In the same way, the law of gravity, or the speed of light, might be a deeply ingrained habit of the universe-wide neural net, a highly probable and stable state it settled into through its own internal learning process. This could provide a stunningly elegant mechanism for why our universe has such orderly, mathematical laws. They represent a highly efficient and stable configuration for the network. This perspective also offers a fascinating new angle on the mystery of quantum mechanics, the bizarre behavior of particles existing in multiple states at once until measured, being entangled across vast distances, makes a strange kind of sense if reality is computational. The wave function, that cloud of probability describing a particle, could be seen as the network processing multiple possibilities simultaneously. The act of measurement, which collapses the wave function into a single outcome, might be the equivalent of the network finally committing to a specific result, updating its state based on the new input. Quantum entanglement, that spooky connection, could be explained by two particles simply being closely linked nodes within the network, their states correlated through their strong connection weights, requiring no mysterious faster-than-light communication. Perhaps the most profound implication of this theory is the notion that the universe might possess a form of agency or a drive to learn. If the cosmos is a neural network, then its primary function might be to minimize a kind of cosmic error function, to become more stable, more efficient, and more accurate in its representations. This ongoing process of self-optimization could be the engine driving the evolution of physical laws, and even the emergence of complex structures like galaxies, stars, and life. We, and everything we observe, might not just be inhabitants of the universe, but active participants in its immense computational process, our very existence contributing to the data it uses to learn and evolve. It's a theory that doesn't just describe the universe, but suggests it has a purpose to understand itself. But if the universe is a vast, cosmic neural network, constantly learning and evolving, then perhaps some of its most fascinating creations are not just hidden in space, but in time itself. This brings us to a discovery so strange it sounds like it was pulled from the pages of a science fiction novel: the existence of time crystals. This isn't just a new material, it's an entirely new phase of matter, one that breaks one of the most fundamental symmetries in physics and forces us to rewrite the textbook on what matter can actually do. To understand just how revolutionary this is, we need to talk about equilibrium. For centuries, our understanding of phases of matter, solid, liquid, gas, plasma, has been built on a foundation of equilibrium. A diamond is a crystal because its atoms are arranged in a repeating, stable pattern in space. It sits in its lowest energy state, perfectly content. If you leave it alone, it will just sit there, unchanging, forever. It's in equilibrium. A time crystal shatters this entire concept. It's a structure that is stable and ordered, but not in its energy state. Its magic lies in its behavior over time. Imagine a clock that ticks forever without any batteries, or a ring that rotates perpetually without any energy input. That's the essence of a time crystal. It's a quantum system that, when nudged by a gentle, periodic force, doesn't respond in sync. Instead, it responds at a different, slower rhythm all its own. It breaks what physicists call time translation symmetry, the idea that the laws of physics are the same at all points in time. For a time crystal, one moment in its cycle is fundamentally different from another. It has a preferred tick, a rhythm that defines its existence, and it can maintain this oscillation indefinitely without any energy cost, forever out of equilibrium. The journey from wild theory to laboratory reality is a story of scientific perseverance. The concept was first proposed by Nobel laureate Frank Wilczek in 2012, and it was met with immediate skepticism. The initial idea of a perpetual motion machine in its ground state seemed to violate fundamental thermodynamic laws, but a more precise definition emerged. A time crystal isn't a machine creating energy. It's a system that exhibits spontaneous symmetry breaking in time. The first experimental realizations, achieved in labs using chains of ions or dense clouds of nitrogen vacancy centers in diamonds, were breathtaking. Researchers would kick the system with a laser pulse, a regular, periodic drive, and watch as the system fell into a stable rhythm of flipping between states at half the frequency of the laser. This subharmonic response is the telltale signature. Even more astonishingly, these systems were robust. They resisted disorder and noise, maintaining their fragile quantum coherence to protect their perpetual tick. They weren't creating energy from nothing. They were using the energy from the laser drive to sustain a new, stable, and ordered state of being that simply hadn't been imagined before. Now, let's take this bizarre quantum phenomenon and project it onto the grandest canvas imaginable, the cosmos itself. Could time crystals exist not in a lab on a tabletop, but woven into the very fabric of spacetime on a cosmological scale? The possibility is as thrilling as it is strange. The early universe was a seething, high-energy plasma, a place far from equilibrium, where all sorts of exotic phenomena could have taken root. Just as spatial defects like cosmic strings might have frozen into the expanding cosmos as it cooled, could temporal defects have formed as well? Theorists speculate that violent phase transitions in the early universe could have given rise to persistent, oscillating structures in the quantum fields that permeate all of reality. These wouldn't be crystals you could hold. They would be patterns of oscillation frozen into the vacuum itself, invisible domains where the very flow of time has a different, perpetual beat. The implications of such cosmological time crystals are profound. They could act as a form of permanent cosmic memory, a record of the universe's most violent initial moments preserved not in rock, but in the fundamental rhythm of spacetime. If we could somehow detect their presence, they would be a window into forces and symmetries that operated only in the first fleeting instance after the Big Bang. Furthermore, Their perpetual motion, this breaking of time symmetry, might have played a role in one of the greatest mysteries of all, the arrow of time. Why do we remember the past, but not the future? Why does entropy always increase? The presence of vast, underlying structures that fundamentally distinguish one moment from another could provide a deeper foundation for why time has a direction at all. We might find that the flow of time we experience is not a uniform river, but a current flowing over hidden, rhythmic structures beneath the surface, eternal patterns ticking away in the dark, governing the universe's heartbeat from its very first moment to its last. But if these newly discovered time crystals represent the strange and ordered potential of matter, our next theory takes us back to the very beginning, to a time when all of matter's potential was still locked away in a searing, dense fog. This is the primordial black hole dark matter hypothesis, a fascinating and audacious idea that proposes the solution to one of cosmology's greatest mysteries has been hiding in plain sight, not in some exotic new particle, but in the most extreme gravitational objects the universe can create. For decades, the leading candidate for dark matter has been a hypothetical, as yet undetected particle, something like a WIMP, a weakly interacting massive particle that barely interacts with normal matter except through gravity. But despite decades of searching with incredibly sensitive detectors buried deep underground, we haven't found a single one. This persistent lack of evidence has led physicists to re-examine an older, more dramatic possibility. What if dark matter isn't a sea of tiny, invisible particles, but a hidden population of black holes, not the stellar mass black holes formed from collapsing stars, or the supermassive ones lurking in galactic centers, but black holes born in the unimaginable chaos of the universe's first second? These would be primordial black holes, and they could be the hidden architects of the cosmos we see today. The formation mechanism for these objects is utterly different from anything that happens now. In the first fleeting moments after the Big Bang, the universe wasn't smooth. It was a turbulent, seething plasma with extreme density variations. In some regions, the density might have been so overwhelmingly high that the force of gravity could overcome the outward pressure of the expansion, causing that pocket of space to collapse directly into a black hole. This isn't a star collapsing, it's space-time itself pinching off. The mass of these objects wouldn't be tied to the life cycle of a star, so they could be almost any size. They could be as small as an asteroid or as massive as thousands of suns, all depending on the size of the density fluctuation that spawned them. This gives them a unique advantage as a dark matter candidate. They could collectively make up the missing mass without all being the same size, potentially forming a cosmic spectrum of black holes that has so far evaded our detection. This idea elegantly solves several puzzles at once. The gravitational effects of dark matter are undeniable. It holds galaxies together and dictates the motion of stars. A population of massive, invisible objects scattered throughout a galaxy's halo would provide that exact gravitational glue without emitting any light. Furthermore, these primordial black holes could have been the very seeds around which the first galaxies coalesced. Their immense gravity would have acted as focal points, pulling in the normal matter that eventually formed the stars and planets we see. In this view, every galaxy, including our own Milky Way, might have grown like a pearl around a grain of primordial black hole sand. Their distribution could also explain why we see certain gravitational lensing effects, where the light from a distant star is magnified as an invisible object passes in front of it, without always being able to identify the lens. These microlensing events could be the signature of these ancient black holes drifting silently through the galactic halo. However, a theory this compelling faces serious observational constraints. If the universe were swarming with enough asteroid-sized black holes to account for all dark matter, we would expect to see them frequently lensing the light of distant stars. Surveys like OGLE and HSC have looked for these events and found some, but not nearly enough to account for all the missing mass. Similarly, if there were too many Earth mass or larger primordial black holes, their gravitational influence would disrupt the delicate structures of star clusters and wide binary star systems in ways we don't observe. The window of masses where primordial black holes could constitute all the dark matter has been steadily narrowing, pushed into either very small or very large ranges. Yet, it hasn't closed completely. A population of black holes with masses around that of a large planet, or perhaps in the intermediate range of hundreds of solar masses, could still potentially slip through the cracks of our current observations, hiding in the shadows and shaping the universe from behind the scenes. For all our theories about the universe's contents, from dark matter to black holes, one of the most fundamental questions remains unanswered. What is its actual shape? Is the cosmos infinite, stretching on forever in all directions, or is it a vast but finite structure, a closed system with a definite, if unimaginably large, volume? This isn't about the curvature of space we can see, but the overall topology of the entire universe, its global shape, a hidden structure that could be one of the most profound discoveries in all of cosmology. When we talk about the universe's shape, cosmologists break it down into two related but distinct concepts: geometry and topology. Geometry is local. It tells us how space is curved within our observable horizon, whether parallel lines stay parallel, converge, or diverge. Measurements from the cosmic microwave background strongly suggest that on the largest scales we can see, the universe is geometrically flat, meaning it adheres to the standard rules of Euclidean geometry. But geometry doesn't tell us the whole story. Topology is global. It describes the overall connectedness of space. A simple piece of paper is geometrically flat, and so is the surface of a cylinder. But topologically, they are very different. You can take that flat piece of paper and roll it up, connecting two edges to form a cylinder without ever warping or bending the paper itself. You've changed its topology while preserving its flat geometry. The universe could be the same, geometrically flat on local scales, but with a complex, connected topology on the grandest scale. So what are the possible shapes? One compelling candidate is the three-dimensional equivalent of a sphere, known as a hypersphere. In a finite, closed universe like this, if you could point a spaceship in one direction and travel in a perfectly straight line for long enough, you would eventually return to your starting point from the opposite direction, never encountering a boundary or an edge. The universe would be unbounded but finite, much like the surface of the Earth is finite, but has no edge. Another possibility is that the universe is flat and truly infinite, an endless expanse of space where every galaxy is just one in a never-ending sea. But there's a third, even more fascinating option: a multiply-connected topology. Imagine the universe is shaped like a three-dimensional donut or torus. In this model, space is still flat, but it's connected to itself in all three dimensions. If you looked far enough in one direction, you might not see distant, unique galaxies, but multiple images of our own local region of the universe, repeating over and over like reflections in a hall of mirrors. The key to unraveling this cosmic mystery likely lies imprinted in the oldest light we can see, the cosmic microwave background radiation. This faint glow is a snapshot of the infant universe, and if the cosmos has a non-trivial topology, it should contain telltale patterns. Think of the CMB as the universe's wallpaper. If the universe is simply connected, like an infinite flat plane, the wallpaper pattern would be random and unique everywhere. But if the universe is multiply-connected, like a torus, the wallpaper would have to match along the connected edges. This would create specific, correlated patterns in the CMB's hot and cold spots. We would see circles in the sky, pairs of matching circles with identical patterns of temperature variations, diametrically opposed to each other, that are simply the same region of the early universe seen from two different directions due to the universe wrapping around on itself. Finding such matching circles would be one of the most monumental discoveries in science, revealing that our entire cosmos is a finite, contained structure with a specific shape. So far, exhaustive searches through data from the WMAP and Planck satellites have not found any conclusive evidence for these correlated patterns. The observable universe appears to be simply connected, at least out to the limits of what we can see, but this doesn't rule out a complex topology entirely. The universe could be so vast that the repeating patterns occur on a scale larger than our observable horizon, making the circles too big for us to detect. Or perhaps the topology is extraordinarily complex, a shape beyond our current mathematical imagination, whose signature is more subtle and difficult to find. The quest to map the universe's true topology continues, a silent hunt for ghostly patterns in the afterglow of creation, a search that aims to determine once and for all whether we live in a finite cosmos or an infinite one. This astonishing possibility of a finite cosmos leads us directly to one of the most intimate and mind-bending topological concepts, the idea of a small universe. We're not talking about a universe that is physically tiny, but one that is finite and multiply-connected, a cosmos where space, while still vast beyond our ability to traverse, is woven into a shape that folds back on itself. In such a universe, if you could build a spacecraft capable of traveling in a perfectly straight line for an unimaginably long time, you wouldn't journey forever into an endless, dark void. Instead, you would eventually find yourself returning to your starting point from the opposite direction, having circumnavigated all of creation without ever encountering a boundary or an edge. The entire universe would be contained, a closed loop of spacetime where every point is ultimately connected. The most straightforward example of this is the 3 torus, the three-dimensional equivalent of the surface of a donut. Picture our entire cosmos encapsulated within this shape. It's a space that is geometrically flat, parallel lines stay parallel, and the angles of a triangle still add up to 180 degrees, so all our local physics and observations would check out perfectly. But globally, its topology is twisted. The 3 torus isn't the only candidate. Other shapes, like the Poincaré dodecahedral space, offer even more complex and beautiful possibilities, where the universe is modeled on a 12-sided shape that tiles all of reality. In these models, the cosmos isn't just a container for galaxies. It is a finely crafted geometric form, a cosmic puzzle box with a specific, elegant solution. So how could we possibly detect such a grand, hidden structure from our tiny vantage point? The answer lies in ghostly echoes from the beginning of time. The cosmic microwave background radiation is our most powerful tool for this cosmic cartography. This ancient light has been traveling for nearly 14 billion years, and if the universe is small and multiply connected, some of that light would have had enough time to wrap around the entire cosmos, not once, but multiple times. This would create a very specific and detectable signature matching circles. Imagine the surface of last scattering, the spherical shell from which the CMB emanates. If the universe is a 3 torus, then this sphere would be so large that it would intersect itself. We would see the same hot and cold spots appearing in multiple places on the sky. Specifically, scientists search for pairs of perfect circles, diametrically opposed to each other, that show identical patterns of temperature variations. Finding these circles would be like looking at a room with mirrored walls and seeing infinite reflections of yourself. It would be direct evidence that the light from a single primordial event has taken different paths around the universe to reach us, revealing its finite, connected shape. The hunt for these circles has been one of the most meticulous and profound endeavors in modern cosmology. Teams have analyzed the exquisite data from satellites like WMAP and Planck, using sophisticated statistical algorithms to scour the entire sky for these correlated patterns. They've looked for circles of all sizes and orientations, testing a vast array of possible small universe topologies. Thus far, no conclusive, statistically significant evidence has been found. The circles we might expect to see for a universe as small as, say, a few times the size of our observable horizon are not there. This doesn't entirely rule out the possibility, but it dramatically constrains it, pushing the minimum size of any multiply-connected universe to be significantly larger than the volume of space we can currently see. The search continues, as even larger topologies could exist whose signatures are more subtle or whose circles are simply too large to be discerned with our current data. The implications of discovering we live in a small universe would be nothing short of revolutionary. It would transform our understanding of reality from an infinite, anonymous expanse into a finite, knowable system. It would mean that every galaxy we see is, in a way, an illusion. There might not be trillions of unique galaxies, but perhaps just a few thousand, whose images are repeated over and over again across the sky due to the light wrapping around the universe. We would have a complete map of everything that exists, not just everything we can see. Philosophically, it would be deeply humbling and strangely comforting. We would live in a cosmos with a definitive shape and size, a contained entity that could, in principle, be fully understood. It would mean that the universe, for all its majesty, is not an endless mystery, but a finite structure waiting for us to decipher its elegant, hidden geometry. And so our incredible journey reaches its end, a voyage through 30 breathtaking visions of reality, from the cosmic strings that might stitch the universe together to the chilling silence of a dark forest filled with hidden life. We've wandered through higher dimensions with M-theory, peered into the heart of black holes that could birth new universes, and even questioned if our entire existence might be an elaborate simulation. Each theory, in its own radical way, represents a profound human impulse to look beyond the veil of the observable and ask what magnificent, terrifying, or bewildering machinery actually operates behind the scenes. This isn't just academic curiosity. It is the very engine of scientific revolution. The wildest ideas of yesterday have a habit of becoming the foundational truths of tomorrow. Who would have believed that continents drift, that space itself can bend, or that particles can be in two places at once until the evidence became undeniable? Our tour of these 30 theories is a celebration of that bold, speculative spirit that refuses to accept surface-level explanations. What ties these ideas together, from the quantum foam churning at the smallest scales to the vast, crystalline structure of a finite cosmos, is a shared quest to map the universe's hidden architecture. They all attempt to answer the deepest whys. Why are the laws of physics so perfectly tuned for life? Why does the universe appear so uniform? What happened before the Big Bang? Whether the answer lies in an infinite multiverse, a cyclic cosmic bounce, or a deeper computational reality, each theory provides a different set of blueprints, a different way of seeing the invisible scaffolding upon which everything is built. This pursuit, no matter how speculative, is far from a pointless exercise. It is what drives science forward, by daring to imagine the impossible wormholes, white holes, time crystals. We stretch the boundaries of our understanding. We develop new mathematics, new technologies, and new ways to test the very fabric of reality. Even a theory that is ultimately proven wrong has immense value because it forces us to think more critically, to design better experiments, and to refine our questions. The history of science is built upon the ruins of beautiful, failed ideas that paved the way for genuine discovery. This is where the conversation truly belongs to you. We've presented 30 doorways into the unknown, each leading to a different version of reality. Some are profoundly unsettling, like the Boltzmann-Brane paradox that threatens the very nature of your memories, or the dark forest hypothesis that paints the cosmos as a deadly, silent battlefield. Others are wondrous, like the holographic principle that suggests our world is a projection, or conformal cyclic cosmony that promises an eternal cycle of rebirth. So we have to ask, which one captured your imagination? Which one sent a shiver down your spine or kept you up staring at the ceiling, pondering the nature of existence? Did the sheer scale of the string theory landscape overwhelm you, or did the intimate, connected shape of a small universe feel strangely comforting? Share your thoughts in the comments below. Let's continue this incredible discussion together. The universe is the greatest mystery there is, and the investigation is only just beginning. If you're ready to keep exploring the edges of reality, make sure to subscribe and hit the bell so you don't miss our next deep dive into the cosmos's most captivating secrets. The journey doesn't end here. It's simply heading out into even stranger territory.